So, the observable universe stretches 93 billion light-years across. That's everything we can see, everything we can measure, everything we've ever observed with our most powerful telescopes. It's incomprehensibly vast, filled with hundreds of billions of galaxies, each containing hundreds of billions of stars. And yet, despite all of that, despite the sheer scale of what we can observe, cosmologists will tell you with a straight face that the observable universe is probably just a tiny, insignificant fraction of the total universe, like not even close. We're talking about a difference so staggering that comparing the Earth to the observable universe would be generous by comparison. Now, when you hear that, your brain probably does what mine did the first time I really thought about it. It asks the obvious question, what the hell is out there beyond what we can see? What lies beyond the edge of the observable universe, beyond this cosmic horizon that marks the limit of everything we can ever hope to observe? And here's where things get properly unsettling, because the answer isn't some simple explanation about more galaxies or more space. No, the answer is far stranger, far more layered, and honestly far more terrifying than that. See, the edge of the universe isn't really an edge at all. It's a boundary we've created for ourselves, a limit imposed by the speed of light and the age of the universe. Light from beyond a certain distance simply hasn't had time to reach us yet, and thanks to the accelerating expansion of space, some of it never will. We're surrounded by a horizon we can never cross, staring out at a cosmos that extends far beyond what we can see, and we're left to wonder what's out there in the dark. Is it more of the same? Is it something completely different? Or is the question itself meaningless? Because once you start pulling at this thread, once you start asking what lies beyond the observable universe, you open the door to ideas that challenge everything you thought you knew about reality. So, let's talk about something that should honestly keep you up at night, the edge of the universe. Now, when I say edge, I'm not talking about some cosmic wall made of bricks or some massive "Do Not Enter" sign floating in space. No, the edge of the universe is far more unsettling than that. It's a boundary we can never cross, not because it's physically blocking us, but because the very nature of reality itself has drawn a line in the sand, and that line? It's called the cosmic horizon. Now, before we dive into the existential dread of it all, we need to establish some groundwork here. The observable universe, the part of the cosmos we can actually see and study, has a radius of about 46.5 billion light-years. That gives us a total diameter of roughly 93 billion light-years. And yeah, I know what you're thinking. Wait a minute, if the universe is only 13.8 billion years old, how the hell can we see stuff that's 46.5 billion light-years away? Shouldn't the edge be like 13.8 billion light-years away? Great question, and honestly, this is where things start to get properly weird. See, the universe isn't just sitting there like some static painting, it's expanding. And not just expanding, but expanding in a way that kind of breaks your brain if you think about it too hard. When we talk about light traveling from distant galaxies to reach us, we're not talking about light making a straight shot from point A to point B on some cosmic highway. We're talking about light traveling through space that is itself stretching and expanding as the light moves through it. It's like trying to run on a treadmill that keeps speeding up the closer you get to the end. Except in this case, the treadmill is the fabric of space-time itself, and you're a photon that's been running for billions of years. So when we say the observable universe has a radius of 46.5 billion light-years, what we're really saying is that the light we're receiving today from the most distant objects has been traveling for 13.8 billion years, but during that time the universe has been expanding. The actual proper distance, accounting for all that expansion between us and those distant objects, is now 46.5 billion light-years. The light has been playing catch-up with an expanding universe, and the numbers reflect that cosmic game of tag. Now, here's where it gets even more mind-bending. Light travels at 186,282 miles per second. That's fast, like incomprehensibly fast. Nothing in the universe can travel faster than light. It's the universal speed limit, the cosmic law that even the most ambitious physicist can't break. But here's the thing, space-time itself doesn't give a damn about that speed limit. Space-time can expand faster than light, and it absolutely does. This isn't some violation of relativity, because relativity governs how objects move through space-time, not how space-time itself behaves. It's a subtle but crucial distinction, and it's the key to understanding why the cosmic horizon exists in the first place. Let's paint a picture here. Imagine you're standing on Earth, looking out into the cosmos with the most powerful telescope ever built. You're peering into the depths of space, seeing galaxies billions of light years away. But there's a limit to what you can see, not because your telescope isn't good enough, but because there's a fundamental boundary to the information that can reach you. That boundary is the cosmic horizon. It's the edge of the observable universe, and it exists because light from beyond that horizon hasn't had enough time to reach us since the Big Bang. Think of it this way. The universe is 13.8 billion years old. That means light has had 13.8 billion years to travel toward us. But because the universe has been expanding this entire time, the actual distance that light has covered in proper terms is much, much farther. The cosmic horizon represents the farthest distance from which light emitted shortly after the Big Bang could have possibly reached us by now. Anything beyond that? We simply can't see it. Not because it doesn't exist, but because the information hasn't had time to get here yet. Now, let's address the elephant in the room here, because I know some of you are probably thinking, okay, so we can't see beyond the horizon right now, but what if we just wait? Won't more light eventually reach us, pushing the horizon farther out? And that's a logical thought, but unfortunately, the universe has other plans. See, the expansion of the universe isn't slowing down, it's speeding up. We've known this since the late 1990s, when observations of distant supernovae revealed that the universe's expansion is accelerating. And this acceleration has some seriously unsettling implications for the cosmic horizon. Because the expansion is accelerating, there's a point beyond which galaxies are receding from us faster than the speed of light. Not because they're physically moving through space at those speeds, but because the space between us and them is expanding at such a rate that the effective recession velocity exceeds light speed. And if a galaxy is receding faster than light, then any light it emits toward us will never reach us. It's like trying to swim upstream in a river that's flowing faster than you can swim. You're moving forward, but the current is dragging you backward even faster. The light is traveling toward us, but the space between us and the source is expanding faster than the light can cover the distance. This brings us to the concept of the cosmic event horizon, which is slightly different from the particle horizon I mentioned earlier. The particle horizon, also called the cosmological horizon or co-moving horizon, is the boundary of the observable universe as it exists right now. It's the farthest distance from which light could have reached us since the Big Bang. The cosmic event horizon, on the other hand, is a bit more forward-looking. It represents the maximum proper distance from which light emitted now will ever reach us in the future. Current models place this event horizon at around 17 billion light-years, give or take, depending on the specifics of the cosmological parameters you're using. What this means is that there are galaxies out there right now that we can see, but if we wait long enough, they'll eventually cross the event horizon and disappear from view forever. Not because they've been destroyed or because they've moved somewhere else, but because the expansion of the universe will have carried them so far away that their light will never reach us again. They'll fade from our telescopes one by one, until eventually the observable universe becomes a much lonelier place. It's a cosmic vanishing act, and there's absolutely nothing we can do to stop it. Now let's talk about the Hubble sphere for a second, because it's another piece of the puzzle here. The Hubble sphere is the region of space within which objects are receding from us at less than the speed of light. The radius of the Hubble sphere is roughly 14 billion light-years, which is smaller than the 5 billion light-year radius of the observable universe. This might seem contradictory at first. How can we see objects that are receding faster than light? Well, the answer lies in the fact that those objects weren't always receding faster than light. When the light we're seeing now was emitted, those galaxies were within the Hubble sphere. They were receding at less than light speed, so their light could make progress toward us. But over time, as the universe expanded, those galaxies crossed the Hubble sphere boundary and are now receding faster than light. The light they emitted in the past, however, had already made enough progress that it could still reach us. It's kind of like a relay race where the baton gets passed just in time. The light left the galaxy when it was still within the Hubble sphere, and even though the galaxy has since crossed into the superfast recession zone, the light was already on its way and could eventually make it to us. But any new light emitted by that galaxy now, that's stuck. It's never going to reach us because the space between us is expanding too fast. So what does all of this mean for the cosmic horizon? Well, it means that the edge of the observable universe isn't a physical barrier. It's not a wall or a force field or some cosmic border patrol keeping us out. It's an information limit. It's the boundary beyond which information, in the form of light, hasn't had the time or the ability to reach us. And because of the accelerating expansion of the universe, that boundary is in many ways a hard limit. There are regions of the universe that we will never ever be able to observe, no matter how advanced our technology becomes or how long we wait. This is a profoundly humbling realization. We like to think of ourselves as explorers, as a species that can eventually go anywhere and see anything if we just try hard enough. But the cosmic horizon tells us that there are fundamental limits to what we can know about the universe. There are places out there, entire galaxies, clusters, superclusters, maybe even structures we can't even imagine, that are forever beyond our reach. Not because we lack the means to get there, but because the very structure of space-time itself has cut us off from them. Now, let's address another question that probably popped into your head at some point during all of this. What's actually out there beyond the horizon? Is it just more of the same, or is it something entirely different? And the honest answer is, we don't know. We can't know, at least not directly. But based on everything we understand about cosmology, the most reasonable assumption is that the universe beyond the horizon looks pretty much like the universe we can see. The cosmological principle, which is one of the foundational assumptions of modern cosmology, states that the universe is homogeneous and isotropic on large scales. In plain English, that means the universe looks roughly the same no matter where you are or which direction you're looking. This principle is supported by observations of the cosmic microwave background, the CMB, which is the afterglow of the Big Bang. The CMB is incredibly uniform, with only tiny fluctuations in temperature across the entire sky. This uniformity suggests that the universe, at least on the largest scales, is pretty much the same everywhere. So if you could somehow teleport to a galaxy 50 billion light-years away, beyond our current cosmic horizon, you'd probably look around and see a universe that looks a lot like ours. Same kinds of galaxies, same kinds of stars, same fundamental laws of physics. But here's the kicker. We can't prove that. We can't observe beyond the horizon to confirm it. We're operating on the assumption that the universe is uniform based on the limited sample we can actually see. It's like being stuck in a small town your entire life and assuming that every other town in the world looks exactly like yours. It's a reasonable assumption based on the information you have, but you can't be 100% certain until you actually go out and check. And in the case of the cosmic horizon, we can never go out and check. We're stuck in our cosmic town, looking out at the horizon and hoping our assumptions are correct. This brings us to a concept that's going to become increasingly important as we move through this video. The idea that the observable universe is just a tiny fraction of the total universe. The 93 billion light-year diameter bubble we can see is, according to most cosmological models, part of a much, much larger space. How much larger, we don't know. It could be 1,000 times bigger. It could be 1,000,000 times bigger. It could be infinite. We literally have no way of knowing because we can't see beyond our cosmic bubble. And this is where things start to get really interesting. Because if the universe is that much larger than what we can see, then what we call the universe is really just our local neighborhood. It's our cosmic backyard. And just like you can't understand the entire planet by only looking at your backyard, we can't understand the true nature of the cosmos by only studying the observable universe. We're limited by our perspective, by the information that can reach us, and by the fundamental laws of physics that govern how light and space-time interact. Now let's take a moment to appreciate just how absurd this situation is. We're sitting here on a tiny rock orbiting an average star in an average galaxy, and we're trying to understand the entirety of existence, and we're doing a pretty damn good job, all things considered. We've measured the age of the universe, mapped out the large-scale structure of galaxies, detected gravitational waves, and even captured images of black holes. But despite all of that incredible progress, we're still fundamentally limited by the cosmic horizon. There's a wall of information we can't cross, a boundary we can't see beyond, and it's dictated by the speed of light and the expansion of space-time. It's frustrating, honestly. It's like being handed the world's most complicated puzzle, but being told you can only work on a tiny corner of it. You can see the pieces you have. You can start to figure out the patterns, but you know there's this massive section of the puzzle that you'll never get to touch, and you have to make peace with that. You have to accept that some questions might not have answers, at least not answers we can ever access. But here's the thing. The cosmic horizon isn't just a limit, it's also a clue. It's a signpost pointing us toward deeper questions about the nature of reality. If the observable universe is just a small part of a much larger whole, then what does that larger whole look like? Is it finite or infinite? Is it all the same, or are there variations, different regions with different properties? And if the universe is that big, does it even make sense to talk about the universe as a single entity, or are we dealing with something more complex, more fragmented, more bizarre than we ever imagined? These are the questions that keep cosmologists up at night, and they're the questions we're going to be exploring throughout this video. Because the cosmic horizon, as daunting as it is just the beginning. It's the first layer of the mystery, the first indication that the universe is far stranger and far larger than we ever thought possible. And if we want to understand what lies beyond the edge of the observable universe, we need to start by understanding why that edge exists in the first place. So, to sum it all up, the cosmic horizon is the boundary of the observable universe, sitting at a radius of 46.5 billion light-years. It exists because light from beyond that distance hasn't had time to reach us yet, and thanks to the accelerating expansion of the universe, some of it never will. The horizon isn't a physical wall, it's an information limit, a hard boundary dictated by the speed of light and the expansion of space-time. And while we can reasonably assume that the universe beyond the horizon looks similar to what we can see, we can't prove it. We're stuck in our cosmic bubble, staring out at the edge and wondering what lies beyond. And that brings us to the next uncomfortable truth we need to confront, the idea that the universe doesn't have a center, or rather, that everywhere is the center, which is somehow even more confusing. Because if the observable universe is a bubble, and we're sitting in the middle of it, doesn't that make us the center of the universe? Spoiler alert, no, it doesn't. And understanding why is going to challenge just about every intuitive notion you have about space and location. So, if the cosmic horizon is this boundary that exists because light hasn't had enough time to reach us from beyond a certain distance, then you might be sitting there thinking, okay, so we're at the center of this bubble, right? We're the starting point, and everything else is expanding away from us. That makes us pretty special, doesn't it? And I get why you'd think that. It's a completely natural, intuitive conclusion. You look out in every direction, you see the cosmic horizon sitting roughly the same distance away in all directions, and your brain immediately goes, well, obviously we're in the middle. Except here's the thing, we're not at all, not even a little bit. And this is where cosmology really starts to mess with your head, because the universe doesn't have a center. Or more accurately, every point in the universe is equally valid as the center, which is somehow an even more confusing statement. But stick with me here, because understanding why there's no center to the universe is absolutely crucial to understanding what's going on with cosmic expansion and what might lie beyond the edge of the observable universe. Let's start with the Big Bang, because I think a lot of the confusion about the center of the universe stems from how people conceptualize what the Big Bang actually was. When most people hear Big Bang, they picture some kind of massive explosion happening at a specific point in space, like a bomb going off. There's a central location where the explosion happens, and then all the matter and energy blast outward from that point, filling up the surrounding empty space. It's the same mental model you'd use for any other explosion you've ever seen. Fireworks, dynamite, a Michael Bay movie, whatever. There's a starting point, and then stuff spreads out from there, but that's not what the Big Bang was, not even close. The Big Bang wasn't an explosion in space, it was an expansion of space itself. This is a subtle but absolutely critical distinction, and it's the key to understanding why the universe doesn't have a center. See, when we talk about the Big Bang happening 8 billion years ago, we're not talking about some specific location in the universe where everything began. We're talking about a moment in time when the entire universe, all of space itself, was in an incredibly hot, dense state. And then, everywhere at once, space started expanding. Not expanding into something, just expanding. Space itself was stretching, and it was stretching everywhere simultaneously. There was no central point from which the expansion originated, because the expansion was happening at every point in space at the same time. Now, I know that sounds like absolute nonsense. How can space expand everywhere at once if there's no starting point? Where's it expanding into? And honestly, these are great questions, and they're questions that trip up even people who should know better. But the answer is that space doesn't need to expand into anything. Space isn't embedded in some larger framework or container. Space is the framework. It's the stage on which everything else happens, and the stage itself is getting bigger. To wrap your head around this, let's use one of the classic analogies that cosmologists love to trot out, the expanding balloon. Now, I know analogies can be a bit annoying sometimes, especially when they get overused, but this one is genuinely helpful, so bear with me. Imagine you've got a balloon, and you take a marker and draw a bunch of dots on the surface of the balloon. Each dot represents a galaxy. Now start inflating the balloon. As the balloon expands, all the dots move away from each other. But here's the key part. There's no dot that's at the center of the expansion. Every single dot sees every other dot moving away from it. If you were an ant standing on one of those dots, you'd look around and see all the other dots receding. And if you hopped over to a different dot, you'd see the exact same thing. Every dot is equally valid as the center of the expansion because the expansion is happening uniformly across the entire surface of the balloon. Now, here's where the analogy gets a little tricky, because the surface of the balloon is a two-dimensional space. It's a flat sheet that's been curved into a sphere, but the universe we live in is three-dimensional. We've got length, width, and height, not just length and width. So when we talk about the universe expanding, we're talking about three-dimensional space stretching in the same way that the two-dimensional surface of the balloon is stretching. It's just harder to visualize because we're embedded in that three-dimensional space, so we can't step outside of it and look at it the way we can look at the surface of a balloon. Another analogy that people use is the raisin bread loaf. Imagine you're baking a loaf of bread with raisins in it. As the dough rises, all the raisins move away from each other. If you're a raisin in the middle of the loaf, you see all the other raisins moving away from you. But the same is true for every other raisin in the loaf. Each one sees itself as stationary and all the others moving away. There's no central raisin. The expansion is uniform throughout the entire loaf. These analogies work because they capture the essential idea. The expansion of the universe isn't about stuff moving through space. It's about space itself expanding, carrying everything along with it. And because space is expanding everywhere at once, there's no central point. Every location in the universe has an equally valid claim to being the center, which means that, functionally, there is no center at all. Now, I can already hear some of you pushing back on this. You're probably thinking, okay, but when we look out at the cosmic microwave background, the CMB, we see it surrounding us in all directions. Doesn't that make us the center of the CMB? And again, it's a reasonable thought, but no, it doesn't. The CMB is the afterglow of the Big Bang. It's light that was emitted roughly 380,000 years after the Big Bang, when the universe cooled down enough for atoms to form and for light to travel freely through space. We see that light coming at us from all directions, forming a shell around us at a distance of about 7 billion light-years, accounting for expansion. But here's the thing. Any other observer, anywhere else in the universe, would see the exact same thing. They'd see the CMB forming a shell around them at roughly the same distance. The CMB doesn't indicate a center. It indicates that the universe was once much hotter and denser everywhere, and the light from that era is now reaching us from all directions. It's kind of like being in a fog. If you're standing in a foggy field, you can see a certain distance in every direction before the fog blocks your view. You might think you're at the center of the fog because it surrounds you uniformly, but of course you're not. The fog extends far beyond what you can see, and anyone else standing somewhere else in the field would see the same thing. They'd see fog surrounding them, and they might think they're at the center too. The fog doesn't have a center, and neither does the CMB. This brings us to a concept that's absolutely fundamental to modern cosmology, the Copernican principle. Now, Copernicus was the guy who figured out that Earth isn't the center of the solar system, that we're actually orbiting the sun along with all the other planets. This was a massive shift in perspective, because for centuries people had assumed that Earth was the center of everything. We were special, we were important, the heavens revolved around us. Copernicus came along and said, actually no, we're just one planet among many, and there's nothing particularly special about our position. The Copernican principle takes that idea and extends it to the entire universe. It states that there's nothing special or privileged about our location in the cosmos. We're not at the center, we're not in some unique position. The universe looks roughly the same no matter where you are. This is also called the cosmological principle, and it's one of the foundational assumptions of modern cosmology. It states that, on large enough scales, the universe is homogeneous and isotropic. Homogeneous means it's the same everywhere. Isotropic means it looks the same in every direction. If you could zoom out far enough and look at the universe on the scale of billions of light years, you'd see that galaxies are distributed pretty evenly. There are clumps and voids, sure, but on average, the density of matter is roughly the same no matter where you look. This principle is supported by a ton of observational evidence. The CMB, for example, is incredibly uniform. When we measure the temperature of the CMB in different directions, we find that it varies by only about 1 part in 100,000. That's an absurdly small variation, and it tells us that the early universe was incredibly smooth and uniform. If there was some special central region, some place where the Big Bang happened, we'd expect to see significant differences in the CMB depending on which direction we looked. But we don't. It's the same everywhere within those tiny fluctuations. We also see this uniformity when we look at the large-scale structure of the universe. Surveys of galaxies have mapped out the distribution of matter over enormous distances, and what they find is that, on the largest scales, galaxies are distributed in a relatively uniform way. There are structures like galaxy clusters and superclusters, filaments and voids, but when you average over large enough volumes, the density is consistent. This is exactly what you'd expect if the universe doesn't have a center and if the cosmological principle holds true. Now let's talk about redshift, because this is another piece of evidence that supports the idea of a universe without a center. In 1929, Edwin Hubble made one of the most important discoveries in the history of cosmology. He observed that galaxies are moving away from us, and the farther away a galaxy is, the faster it's receding. This relationship is now known as Hubble's law, and it's usually expressed as velocity equals Hubble's constant times distance. The Hubble constant, which we'll call h0, is a number that tells you how fast the universe is expanding. Current measurements put it somewhere between 67 and 74 kilometers per second per megaparsec, depending on who you ask and what method they used to measure it. There's actually a bit of a controversy about the exact value right now, which cosmologists call the Hubble tension, but that's a topic for another time. The key point is that Hubble's law tells us that the universe is expanding uniformly. Every galaxy is moving away from every other galaxy, and the speed at which they're receding is proportional to the distance between them. This is exactly what you'd expect if space itself is expanding everywhere at once. If the expansion had a center, we'd see a different pattern. We'd see galaxies on one side of us moving away faster than galaxies on the other side, or we'd see some preferred direction in the expansion, but we don't. The expansion looks the same in every direction, which is consistent with there being no center. Hubble's discovery was based on something called redshift. When we look at light from distant galaxies, we find that the wavelengths of that light are stretched, shifted toward the red end of the spectrum. This happens because the space between us and those galaxies is expanding, stretching the light waves as they travel. The farther away a galaxy is, the more space has expanded during the light's journey and the greater the redshift. This redshift is directly proportional to distance, which is why we can use it to infer how far away galaxies are and how fast they're receding. Now, here's the thing that really drives home the point about there being no center. Every galaxy sees the same thing. If you could hop in a spaceship and travel to a galaxy 10 billion light-years away, you'd look around and see all the other galaxies receding from you, just like we do from Earth. You'd measure the same kind of redshifts, and you'd conclude that the universe is expanding uniformly in all directions. You wouldn't see Earth as some special central location from which everything is fleeing. You'd see yourself at the center of your own observable universe, with everything else moving away from you. This is a profound realization, and it's one that really challenges our intuitive sense of location and centrality. We're used to thinking in terms of absolute positions. You're at this location, I'm at that location, and there's some objective framework that defines where everything is. But in an expanding universe, that framework doesn't exist. Position is relative, and every observer has an equally valid perspective. There's no objective center, no preferred location, it's all relative. Now let's address the obvious follow-up question. If the universe doesn't have a center, does it have an edge? And the answer is probably not, at least not in the way you're thinking. When we talk about the edge of the observable universe, we're talking about the cosmic horizon we discussed earlier. That's the limit of what we can see, not a physical boundary, but what about the universe as a whole? Does it have an edge somewhere out there beyond what we can observe? The answer depends on the geometry of the universe, and this is where things get a bit technical, but stick with me. The shape of the universe is determined by its overall density and the way space is curved. There are three basic possibilities. The universe could be flat, meaning it has zero curvature. It could be positively curved, like the surface of a sphere, or it could be negatively curved, like the surface of a saddle. Current observations, particularly from the Planck satellite, suggest that the universe is very close to flat. The curvature parameter, which cosmologists call omega k, is consistent with 0 to within a margin of error of about 0.2%. If the universe is truly flat, then it's likely infinite in extent. There's no edge, space just goes on forever in all directions. If you could travel far enough, you'd never reach a boundary or a wall. You'd just keep going, passing through more and more space filled with galaxies indefinitely. If the universe is positively curved, like the surface of a sphere, then it could be finite but still have no edge. Just like the surface of a balloon has no edge, you can travel around it forever without ever running into a boundary. A positively curved universe would work the same way in 3 dimensions. You could travel in a straight line and eventually end up back where you started, having looped around the entire universe. It sounds bizarre, but it's a perfectly valid solution to the equations of general relativity. If the universe is negatively curved, like a saddle, then it's almost certainly infinite, stretching out forever in all directions with no edge. So regardless of which geometry is correct, the answer is the same. The universe probably doesn't have an edge. If it's flat or negatively curved, it's infinite. If it's positively curved, it's finite but unbounded, meaning you can travel through it forever without hitting a wall. Either way, there's no edge, just like there's no center. Now, I know this is a lot to take in, and it's hard to reconcile with our everyday experience. We're used to things having edges and centers. Your house has a center and edges. Your city has a center and edges. Even the Earth, for all its size, has a center and edges. But the universe plays by different rules. It's not a thing sitting in space, it is space, and space, as far as we can tell, doesn't have a center or an edge. It's either infinite or it curves back on itself in a way that makes edges meaningless. There's a quote from the British astronomer Fred Hoyle that I think sums this up pretty well. Back in 1949, during a BBC radio broadcast, he said, "There is no center of the universe. It is everywhere." Now, Hoyle was actually an advocate of the steady-state theory, which turned out to be wrong, but his statement about the lack of a center is spot on. Every point in the universe is equally valid. Every observer, no matter where they are, sees the universe expanding around them. There's no privileged location, no cosmic capital city, no center stage. Stephen Hawking echoed this idea in his book, A Brief History of Time. He wrote, "The universe is the same for all observers. No point is more central than any other." This is the essence of the cosmological principle, and it's one of the most important insights in all of cosmology. It tells us that we're not special. Our location isn't special. The view we have of the universe is the same view that any other observer would have from any other location. We're all equally unimportant when it comes to cosmic geography. Now, here's where things get even weirder, and this is something that's going to become really important as we move forward in this video. If every point in the universe is equally valid as the center, and if the universe is either infinite or curves back on itself, then what does that say about the observable universe? Well, it tells us that the observable universe is just a tiny, tiny bubble within a much larger whole. Our cosmic horizon, that 46.5 billion light-year radius, is just the limit of what we can see. It's not the limit of what exists. Beyond that horizon, there's more universe. How much more? We don't know. If the universe is infinite, then the answer is infinitely more. If it's finite but very large, then it could be thousands or millions of times bigger than what we can observe. And here's the kicker. Every other observer in the universe has their own observable universe, their own cosmic bubble. Those bubbles overlap with ours to some degree, but they also extend beyond our horizon. There are regions of space that are within their observable universe but not within ours, and vice versa. It's like a Venn diagram of cosmic visibility, with each observer sitting at the center of their own circle, unable to see beyond their own horizon. This has some pretty wild implications. It means that there are galaxies out there, entire clusters and superclusters that we will never be able to see, not because they're hidden behind something, but because the light from them hasn't had time to reach us yet. And thanks to the accelerating expansion of the universe, it never will. Those regions of space are, in a very real sense, completely cut off from us. They're part of the same universe, governed by the same laws of physics, filled with the same kinds of stars and galaxies. But we can never observe them, never study them, never visit them. They're forever beyond our reach. And the same is true in reverse. There are regions of space where observers can see things that we can't. From their perspective, we're the ones who are beyond the horizon, invisible and unreachable. It's a humbling thought, and it really drives home the point that the universe is so much bigger than the little bubble we can see from Earth. So, to sum it all up, the universe doesn't have a center because the Big Bang was an expansion of space itself, happening everywhere at once. Every point in the universe is equally valid as the center, which means there is no center at all. The cosmological principle tells us that the universe is homogeneous and isotropic on large scales, meaning it looks the same no matter where you are or which direction you're looking. Hubble's law and the observation of galactic redshifts confirm that the universe is expanding uniformly with no preferred location. And depending on the geometry of the universe, it's either infinite in extent or finite but unbounded, meaning there's no edge. Every observer sits at the center of their own observable universe, a bubble roughly 93 billion light-years across, surrounded by a cosmic horizon beyond which they cannot see. This is a radically different picture of the universe than the one most people carry around in their heads. We're not at the center. We're not in a special location. We're just one observer among countless others, each with their own perspective, each surrounded by their own horizon. And beyond those horizons, the universe continues, possibly forever, filled with galaxies and structures we'll never be able to observe. And that brings us to the next big question. If the observable universe is just a tiny bubble within a much larger whole, what does that larger whole look like? Is it all the same, or are there differences, variations, regions with different properties? And if the universe extends far beyond what we can see, possibly infinitely, what does that mean for the nature of reality itself? Because once you start thinking about a universe that's vastly larger than the observable universe, you open the door to some pretty wild ideas. Ideas about infinite space, infinite possibilities, and structures that make our entire observable universe look like a grain of sand on a cosmic beach. And that's exactly where we're headed next. So we've established that the observable universe is this 93 billion light-year wide bubble, that there's no center to the universe, and that every observer sits in the middle of their own cosmic horizon. But here's where things get properly mind-bending, because the observable universe, this massive bubble we've been talking about, is almost certainly not the entire universe. In fact, it's probably just a tiny, insignificant fraction of the total universe. And when I say tiny, I mean incomprehensibly, absurdly, laughably tiny. We're talking about a scale difference that makes the Earth compared to the observable universe look like a generous ratio. Now, before we dive into just how much bigger the universe might be than what we can see, we need to make a crystal clear distinction between two concepts that people often confuse: the observable universe and the actual universe. The observable universe, as we've discussed, is the region of space from which light has had time to reach us since the Big Bang. It's defined by our cosmic horizon, and it has a radius of about 46.5 billion light years. That's big, that's incomprehensibly big, but it's a finite size, and more importantly, it's a size defined entirely by our position and our limitations as observers. The actual universe, on the other hand, is everything that exists. It's the totality of space and everything in it, regardless of whether we can observe it or not. And here's the kicker. We have absolutely no idea how big the actual universe is. It could be 1,000 times bigger than the observable universe. It could be 1,000,000 times bigger. It could be 1,000,000,000 times bigger. Or, and this is where things get really wild, it could be infinite, just infinite. No edges, no boundaries, space extending forever in all directions, filled with galaxies and stars and planets and whatever else is out there, going on literally forever. Now, I know that concept, infinity, is hard to wrap your head around. It's hard for everyone, even professional cosmologists who work with this stuff every day. Our brains didn't evolve to comprehend infinity. We're used to things that have limits, boundaries, endpoints. But in cosmology, infinity isn't just some abstract mathematical concept. It's a real possibility, maybe even the most likely possibility, for the nature of the universe we live in. So let's talk about why cosmologists think the universe might be infinite, or at the very least, vastly larger than what we can observe. The story starts with a problem, as most good scientific stories do. Back in the late 1970s and early 1980s, cosmologists were grappling with a set of puzzles about the early universe that didn't quite add up. One of the biggest puzzles was something called the horizon problem, which, funnily enough, we sort of touched on earlier when we were talking about the cosmic horizon. Here's the issue. When we look at the cosmic microwave background, the CMB, we find that it's incredibly uniform. The temperature is the same in every direction to within about 1 part in 100,000. That's an absurdly high level of uniformity. Now, why is that a problem? Well, the CMB shows us what the universe looked like about 380,000 years after the Big Bang, when it was cool enough for atoms to form and light could travel freely. When we look at 2 points on opposite sides of the sky, we're looking at regions of space that were, at that time, separated by such a vast distance that light couldn't have traveled between them in the time available. They were beyond each other's cosmic horizons. They were causally disconnected. But if they were causally disconnected, how did they end up at the same temperature? How did they know to be so incredibly uniform? It's like walking into 2 completely separate rooms that have never been connected and finding that both rooms are exactly 72 degrees Fahrenheit. How did they coordinate? How did they reach the same temperature without any way to exchange heat or information? This was the horizon problem, and it was a real thorn in the side of cosmologists. The universe shouldn't be this uniform if the Big Bang was just a straightforward expansion from a hot, dense state. There should be more variation, more differences between regions that were never in contact with each other. But instead, we see this remarkable smoothness, and nobody could explain why. Enter a physicist named Alan Guth. In 1980, Guth proposed a radical solution to the horizon problem. He suggested that in the very earliest moments of the universe, specifically in the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion. Not just regular expansion, but exponential expansion, where the size of the universe doubled over and over again in an incredibly short period of time. He called this process cosmic inflation, and it's one of the most important ideas in modern cosmology. Here's how inflation solves the horizon problem. Before inflation, the entire observable universe we see today was once a tiny, tiny region of space. And I mean tiny. We're talking about a region smaller than an atom. In this tiny region, everything was in thermal contact. Everything could exchange energy and information, so everything reached the same temperature. Then, boom, inflation kicks in. This tiny region expands exponentially, growing to an enormous size in a fraction of a second. By the time inflation ends and the universe returns to normal expansion, this tiny uniform region has been blown up to encompass a volume far larger than what we can observe today. So the reason the CMB is so uniform is because it all came from a single tiny patch that was in thermal equilibrium before inflation. Inflation took that patch and stretched it out to enormous size, preserving the uniformity. It's like taking a tiny section of wallpaper with a smooth pattern and stretching it across an entire wall. The pattern stays smooth because it all came from the same source. Problem solved. But inflation doesn't just solve the horizon problem. It also solves another major puzzle called the flatness problem. Remember when we talked about the geometry of the universe and how current observations suggest it's very close to flat? Well, a flat universe is actually a really special case. If the universe started out even slightly curved, either positively or negatively, that curvature would have grown dramatically over time as the universe expanded. For the universe to be as flat as we observe it today, it would have had to be extraordinarily, almost impossibly flat in the early universe. It's like balancing a pencil on its tip. You'd have to get the initial conditions exactly right for it to stay balanced, and even the tiniest deviation would cause it to fall over. Inflation solves this problem by stretching space so much that any initial curvature gets smoothed out. It's like taking a wrinkled bedsheet and pulling it tight. The more you stretch it, the flatter it looks. Even if the universe started out with significant curvature, inflation would have stretched it so much that the curvature became negligible. From our perspective, sitting in a tiny region of this vastly expanded space, the universe looks flat because we're seeing such a small fraction of it. It's the same reason the Earth looks flat when you're standing on the surface. You're only seeing a tiny piece of a much larger sphere, so the curvature is imperceptible. Now, the fact that inflation predicts a flat universe is actually one of the main reasons cosmologists take the theory so seriously. When Guth first proposed inflation, the data on the universe's curvature wasn't very precise. But as observations improved, particularly with satellites like COBE, WMAP and Planck, the measurements kept coming back with the same result. The universe is flat to within a fraction of a percent. Inflation predicted this, and the observations confirmed it. That's a huge win for the theory. But here's where things get really interesting, because a flat universe has some pretty wild implications. In general relativity, a flat universe is spatially infinite. It doesn't curve back on itself like a sphere, so there's no reason for it to have an edge or a boundary. It just goes on forever. Now, there are some caveats here. A flat universe could, in principle, have a weird topology. It could be like a cylinder, which is flat but finite, wrapping around on itself in one direction. But unless there's something very unusual going on, the simplest interpretation of a flat universe is that it's infinite in extent. So if the universe is flat, and if flat means infinite, then the actual universe is infinite, not just really big, not just unimaginably vast, but literally infinite. There is no edge, there is no end. Space goes on forever, filled with galaxies and stars and planets, extending infinitely in all directions, and our observable universe, this 93 billion light-year-wide bubble we've been talking about, is an infinitesimally small piece of that infinite whole. Now, I want to pause here and let that sink in for a second, because this is one of those ideas that's so big it's hard to fully process. If the universe is infinite, then everything we can see, everything humanity has ever observed or studied or theorized about, all of it, is contained within a bubble that represents exactly 0% of the total universe. You can't even calculate the ratio because the denominator is infinity. Our observable universe is literally infinitesimal compared to the whole. And here's where things get even weirder, because if the universe is infinite and the laws of physics are the same everywhere, then statistically, everything that can happen will happen. Not just once, but infinitely many times. There are infinitely many galaxies out there, infinitely many stars, infinitely many planets. And if you go far enough, you'll eventually find another planet exactly like Earth, with the same continents, the same oceans, the same history. You'll find another version of you, sitting in a room exactly like the one you're in right now, listening to the exact same video. And there are infinitely many copies of you out there, living infinitely many variations of your life. This isn't science fiction. This is a direct consequence of an infinite universe combined with quantum mechanics and probability. If space is infinite and matter is distributed roughly evenly, then every possible arrangement of particles will occur somewhere. And since there are only a finite number of ways to arrange particles within a given volume, those arrangements will repeat. The math is pretty straightforward. If you've got an infinite universe and a finite number of possible configurations, you're going to get repeats, lots of them, infinitely many of them. The cosmologist Max Tegmark has written about this extensively. He calculated that if the universe is infinite, there should be an exact copy of you about 10 to the power of 10 to the power of 29 meters away. That's a 1 followed by 10 billion trillion zeros. It's a number so big it doesn't even make sense. You couldn't write it down if you used every atom in the observable universe as a digit. But in an infinite universe, it's not just possible, it's inevitable. There's another you out there, and there are infinitely many of them. Now, before you start freaking out about your infinite doppelgangers, let me clarify something. These copies are so far away that you'll never interact with them. They're beyond the cosmic horizon, in regions of space that are receding from us faster than light. You can't reach them, you can't communicate with them, you can't even observe them. They're part of the same universe, but they might as well be in a completely separate reality for all the difference it makes to you. The accelerating expansion of the universe ensures that these distant regions will remain forever out of reach. But the point is, if the universe is infinite, then it's not just big, it's infinite. And infinity has consequences that are hard to wrap your head around. It means that everything that can happen does happen somewhere. Every possible history, every possible configuration of matter, every possible version of reality, all of it exists somewhere in the infinite expanse of space. Now you might be wondering at this point, okay, but do we actually know the universe is infinite? And the honest answer is no, we don't, we can't. The only way to definitively prove the universe is infinite would be to observe the entire thing, and that's obviously impossible. We're stuck inside our cosmic bubble, and we can't see beyond the horizon. But we can make some educated guesses based on the data we do have. The strongest evidence comes from measurements of the universe's curvature. As I mentioned earlier, the Planck satellite has measured the curvature parameter omega k to be consistent with 0 to within about 0.2%. That means the universe is flat, or at least so close to flat that we can't detect any curvature. And a flat universe, as we've discussed, is most naturally interpreted as infinite. But here's the thing, just because we can't detect curvature doesn't mean there isn't any. It's possible that the universe is very slightly curved, but the curvature is so small that it's below our detection threshold. If that's the case, the universe could be finite but just enormously large, far larger than the observable universe, but not infinite. Think of it like standing on a really, really big sphere. The surface looks flat to you because you're only seeing a tiny fraction of it. But if you could zoom out far enough, you'd see that it does curve back on itself. So while the data suggests the universe is flat and therefore likely infinite, we can't rule out the possibility that it's just really, really big instead. Either way, the conclusion is the same for practical purposes. The universe extends far, far beyond what we can observe, and there are vast regions of space out there that we'll never be able to see or reach. Now let's talk about what might be out there beyond our cosmic horizon, because even if we can't observe it directly, we can make some educated guesses based on what we do know. The cosmological principle, which we talked about in the last chapter, tells us that the universe should look roughly the same no matter where you are. If that's true, then the universe beyond our horizon probably looks a lot like the universe we can see. More galaxies, more stars, more planets, all arranged in the same large-scale structures we observe here. Galaxy clusters, superclusters, filaments, voids, all of it repeating in an endless cosmic tapestry. But there's a catch. The cosmological principle only applies on the largest scales, and even then it's an approximation. On smaller scales, the universe is lumpy and irregular. We've got dense regions with lots of galaxies and sparse regions with very few. We've got massive structures like the Great Wall, a collection of galaxies spanning hundreds of millions of light years. We've got the Bhuta's Void, a region of space about 330 million light-years across that's almost completely empty. So while the universe is homogeneous on average, there's a lot of local variation. This means that when we talk about what's beyond the horizon, we can say with some confidence that it's probably similar to what we see here, but we can't predict the details. There might be regions with even larger structures than anything we've observed. There might be regions that are unusually dense or unusually sparse. There could be variations in the properties of dark matter or dark energy that we haven't accounted for. We just don't know, and we can't know without direct observations. One particularly interesting idea is something called dark flow, which is a hypothesized phenomenon where galaxy clusters appear to be moving in a particular direction at high speeds, as if they're being pulled by some massive gravitational source beyond the edge of the observable universe. The evidence for dark flow is controversial, and many cosmologists are skeptical. But if it's real, it would suggest that there are enormous structures just beyond our cosmic horizon, massive concentrations of matter that are exerting gravitational influence on the galaxies we can see. Imagine if dark flow is real and there's some gargantuan superstructure out there, something so massive that it's pulling entire galaxy clusters toward it. That would tell us that the universe beyond our horizon isn't just more of the same. It would tell us that there are features, structures, concentrations of matter on scales we haven't even begun to comprehend. It would be a reminder that our observable universe, as vast as it is just a tiny window into a much, much larger cosmos. Now, even if dark flow turns out to be a fluke, the basic point stands. The universe beyond the horizon is probably filled with wonders and structures we can't even imagine. There could be galaxy superclusters that dwarf anything we've observed. There could be voids so large they make the Bootes void look like a pothole. There could be regions where the density of matter is significantly higher or lower than average, creating environments utterly unlike anything in our cosmic neighborhood. And here's the really humbling part. We'll never know. Those regions are forever beyond our reach, cut off from us by the expansion of space. They're part of the same universe, but they might as well be in another dimension for all the difference it makes. We can theorize, we can speculate, we can extrapolate from what we see, but we can never observe them directly. They're the ultimate unknown, the cosmic terra incognita that will remain forever on the edge of our maps. This brings us back to inflation, because inflation doesn't just explain why the observable universe is so uniform and flat. It also tells us something about the scale of the total universe. During inflation, the universe expanded exponentially, doubling in size over and over again in a tiny fraction of a second. The exact number of doublings depends on the details of the inflationary model, but most models predict at least 60 doublings, which is often called 60 e-folds. Each e-fold represents a doubling in size, so 60 e-folds means the universe expanded by a factor of 2 to the power of 60. Now, 2 to the power of 60 is a big number. It's about a billion, or 10 to the power of 18. But here's the kicker, that's just the minimum. Many inflationary models predict far more than 60 e-folds, possibly hundreds or even thousands, and each additional e-fold doubles the size again. So even if the observable universe was only a tiny fraction of the total universe before inflation, after inflation it became an infinitesimally tiny fraction. To put this in perspective, imagine you've got a grain of sand. Now inflate it by 60 e-folds, and it becomes larger than the observable universe. Inflate it by 100 e-folds, and it's incomprehensibly larger. Inflate it by 1,000 e-folds, and you're dealing with numbers that make infinity look almost reasonable. The scale of the universe after inflation is so vast that our observable universe is less than a single atom compared to the whole. We're not even a rounding error. We're a rounding error of a rounding error of a rounding error. This is one of the reasons cosmologists think the universe is either infinite or at least so large that it might as well be. If inflation happened, and all the evidence suggests it did, then the total universe must be unimaginably vast. Our observable bubble is just one tiny patch in an ocean of space so large we can't even comprehend it. And here's where things start to get really strange, because if inflation can happen once, why couldn't it happen multiple times? What if inflation didn't happen everywhere at once, but instead happened in different regions at different times? What if our universe, the entire infinite expanse of space we've been talking about, is just one bubble in a much larger multiverse, where each bubble is its own universe with its own properties and its own laws of physics? This is the idea of eternal inflation, and it's one of the most profound and controversial concepts in modern cosmology. It takes everything we've talked about, the observable universe, the horizon, the infinite expanse of space, and it makes it all seem small by comparison. Because if eternal inflation is real, then our universe, infinite as it may be, is just one bubble in an infinite sea of bubbles, each one a separate cosmos with its own history, its own stars, its own galaxies, and possibly its own versions of you and me. And that's where we're headed next, into the bizarre, mind-bending territory of eternal inflation and the multiverse. Because if you thought an infinite universe was hard to wrap your head around, Just wait until we start talking about infinitely many infinite universes. So, we've talked about inflation, this period of exponential expansion that happened in the first fraction of a second after the Big Bang. We've talked about how it solves major problems in cosmology, like the horizon problem and the flatness problem. We've talked about how it stretched our universe from something smaller than an atom to something vastly larger than what we can observe today. But here's where things get absolutely wild, because inflation, as it turns out, might not have been a one-time event. In fact, according to some of the most brilliant minds in cosmology, inflation might still be happening right now. Not here, not in our universe, but out there, in regions of space we can't observe, regions that are so far away they might as well be in another dimension. This is the idea of eternal inflation. And if it's true, then our universe, this entire infinite expanse of space we've been talking about, is just one bubble in an infinite ocean of bubbles, each one a separate cosmos with its own properties, its own history, and possibly its own laws of physics. Now, before you write this off as science fiction or the ramblings of physicists who've spent too much time staring at equations, let me be clear: eternal inflation is a serious, well-studied theory that has significant support within the cosmological community. It's not fringe science. It's a natural extension of the inflationary model that already explains so much about the universe we observe. And it has some seriously mind-bending implications that we're going to dive into in this chapter. The story of eternal inflation begins, like many good stories in cosmology, with a problem. Standard inflation, the kind proposed by Alan Guth back in 1980, was great at solving the horizon and flatness problems, but there was a question that kept nagging at physicists: what exactly caused inflation to end? The basic idea of inflation is that the early universe was filled with a scalar field called the inflaton. This field had a ton of potential energy, and that energy drove the exponential expansion. But at some point, the inflaton field had to decay to transition from this high-energy state to a lower-energy state, releasing its energy and reheating the universe. This process, called reheating, is what ended inflation and created all the matter and radiation we see today. It's basically the bridge between inflation and the hot Big Bang. But here's the thing: quantum mechanics tells us that fields don't all decay at the same time. It's a probabilistic process. Think of it like radioactive decay. If you've got a chunk of radioactive material, you can calculate its half-life, the time it takes for half of it to decay, but you can't predict exactly when any individual atom will decay. It's random. The inflaton field works the same way. Different regions of space would decay at different times, purely by chance. Some regions would decay quickly, ending inflation and forming what we'd recognize as a universe. But other regions, they'd keep inflating. And here's where it gets really interesting. Inflation is exponential, which means it's extremely fast. If a region is still inflating, it's doubling in size over incredibly short timescales. Even if most of the inflaton field has decayed and stopped inflating, the regions that are still inflating grow so quickly that they dominate the total volume. It's like trying to empty a bathtub while the faucet is running at full blast. Yeah, water is draining out, but it's being replaced faster than you can remove it. The tub keeps filling. This is the core insight behind eternal inflation. Once inflation starts, it's really, really hard to stop it everywhere. You can have regions where it ends, and those regions become pocket universes, bubble universes, little oases of normal space where inflation has stopped and matter can form. But the space between those bubbles, it's still inflating, still expanding exponentially, and it's creating more and more volume where new bubbles can form. The process never stops. It goes on forever, creating an infinite number of bubble universes within an eternally inflating background space. The physicist André Linde was one of the key figures in developing this idea. In the early 1980s, Linde modified Guth's original inflationary model to create what he called new inflation. And then in 1986, he took it a step further with chaotic inflation. Chaotic inflation is based on the idea that the early universe wasn't uniform. Different regions had different values of the inflaton field. Some regions had high field values and inflated like crazy. Other regions had low field values and didn't inflate much, or at all. But because inflation is exponential, the regions that did inflate quickly came to dominate the total volume. They became the observable universe, or rather, one of many observable universes. Linde's key realization was that inflation doesn't need special initial conditions. You don't need to fine-tune the starting state of the universe to get inflation to happen. Chaotic inflation says that inflation is a natural, almost inevitable consequence of the physics of scalar fields. Somewhere in the mess of the early universe, conditions were right for inflation to start, and once it started, it took over. And not just in one place, but in infinitely many places, each creating its own bubble universe. Now, I want you to picture this because the visual is actually really helpful. Imagine a vast ocean, except instead of water, it's space that's inflating exponentially. This is the eternally inflating background. Now, within this ocean, bubbles are forming. Each bubble is a region where the inflaton field has decayed and inflation has stopped. Inside each bubble, you've got a pocket universe, a region of space that looks like what we call a universe. It's got matter, radiation, galaxies, stars, maybe even planets and life. But the space between the bubbles, that's still inflating, still growing, and new bubbles are constantly forming within it. This isn't a one-time process, it's eternal. It goes on forever, both into the future and, depending on how you interpret the math, possibly even into the past. The ocean of inflating space keeps expanding, and bubbles keep nucleating within it, over and over, infinitely. Each bubble is causally disconnected from the others because they're separated by regions of space that are inflating faster than light. Once a bubble forms, it can never interact with another bubble. They're separate universes in the most literal sense of the word. Alexander Vilenkin, another major figure in the development of eternal inflation, put it this way: inflation did not occur everywhere at once. But those domains where inflation does take place become exponentially large and dominate the universe. That's the key. It doesn't matter if inflation only happens in a small fraction of the initial space, because the regions where it does happen grow so fast that they overwhelm everything else. And within those inflating regions, more bubbles form, and the cycle continues forever. Now, let's talk about the math for a second, because the math is what convinced cosmologists that eternal inflation wasn't just a speculative idea, but a real, potentially unavoidable consequence of inflation. In 1983, Paul Steinhardt, André Linde and Alexander Vilenkin independently worked out the mathematics of eternal inflation and came to the same conclusion: if the decay rate of the inflaton field is slower than the expansion rate, then inflation will continue forever in some regions. You can't stop it everywhere. It's a runaway process. Think of it like a game of whack-a-mole. You can hit one mole and it goes down. That's a bubble universe forming, a region where inflation stops. But while you're hitting that one, two more pop up somewhere else, and then four more, and then 8, you're always going to have moles popping up faster than you can whack them down. Inflation is like that. Bubbles form, but the inflating space is creating new volume faster than bubbles can fill it. The game never ends. This has some seriously profound implications. If eternal inflation is real, then our universe, this entire expanse of space that might be infinite in its own right, is just one bubble among infinitely many. There's nothing special about it. It's not the universe. It's a universe. One pocket of space where inflation happened to stop, conditions happened to be right for matter to form, and galaxies and stars and planets happen to coalesce. But there are infinitely many other bubbles out there, each with their own history, their own contents, and possibly their own physical laws. And that last part is where things get really interesting, because there's no reason to think that all bubbles are the same. In fact, there are very good reasons to think they're different. Let me explain. In physics, we talk a lot about constants, the speed of light, the strength of gravity, the mass of the electron, the fine structure constant. These are the numbers that define how the universe works. They're the settings, the parameters that determine what kinds of structures can form, what kinds of chemistry is possible, what kinds of life can exist. And for the most part, we treat these constants as fixed. They are what they are, and we don't really have a good explanation for why they have the values they do. They just do. But here's the thing, in many models of eternal inflation, especially those that incorporate ideas from string theory, which we'll get to in a later chapter, these constants aren't constant across all bubbles. They're environmental. They're a result of how the inflaton field decayed in that particular bubble, what energy state it settled into, what configuration the underlying physics ended up in. It's like different bubbles landed on different settings when the inflaton field rolled down to its minimum energy state. Think of it like rolling dice. Every time a bubble forms, the physics of that bubble rolls the dice on what the fundamental constants will be. Most of the time, you're going to get values that don't allow for interesting structures. Maybe gravity is too strong, and everything collapses into black holes immediately. Maybe the electromagnetic force is too weak, and atoms can't hold together. Maybe the cosmological constant is huge, and the universe expands so fast that matter can never clump together to form galaxies. These bubbles are duds. They're boring. They don't have stars. They don't have planets. They don't have life. But every once in a while, you roll the dice and you get a combination that works. Gravity is strong enough to pull matter together, but not so strong that everything collapses. The electromagnetic force is just right for atoms to form and chemistry to happen. The cosmological constant is small enough that the universe expands slowly enough for galaxies to form. You get a bubble like ours, where the conditions are right for complexity, for structure, for life. This is called the anthropic principle, and it's one of the most controversial ideas in cosmology. The basic idea is that we observe the universe to have the properties it does, because if it didn't have those properties, we wouldn't be here to observe it. It's a selection effect. Out of the infinite number of bubbles in the eternally inflating multiverse, we necessarily find ourselves in one of the rare bubbles where the conditions allow for observers to exist. It's not that our bubble is special or fine-tuned by some cosmic designer. It's that we couldn't possibly find ourselves in a bubble that doesn't allow for life, because there'd be no one there to do the finding. Now, a lot of people hate the anthropic principle. They think it's a cop-out, a way of avoiding the hard work of actually explaining why the constants have the values they do. And I get that criticism. It does feel a bit unsatisfying to just say, well, it is what it is, because if it wasn't, we wouldn't be here. It's not a predictive explanation. It doesn't tell you what the constants should be. It just says they have to be in a range that allows for observers. But here's the thing, if eternal inflation is real, and if different bubbles really do have different physical constants, then the anthropic principle isn't a cop-out. It's the answer. There's no deeper explanation for why our universe has the constants it does. It's just chance. We rolled the dice and got a good combination. There are infinitely many other bubbles that rolled different combinations, and most of them are empty, sterile wastelands. But we're not in one of those. We're in one of the rare bubbles where things worked out, and that's why we're here to ask the question in the first place. This has a direct bearing on one of the biggest puzzles in cosmology, the fine-tuning problem. Our universe appears to be fine-tuned for life in some really uncanny ways. The cosmological constant, for example, which determines the rate at which the universe's expansion is accelerating, has a value that's absurdly small. Quantum field theory predicts it should be huge, something like 10 to the power of 120 times bigger than what we observe. If it were that big, the universe would have expanded so fast that galaxies could never have formed. But it's not. It's just barely above zero, small enough that the universe expanded slowly for billions of years, allowing matter to clump together and form the structures we see today. Why is the cosmological constant so small? Nobody knows. It's one of the biggest unsolved problems in physics. But if eternal inflation is real, and if different bubbles have different values of the cosmological constant, then the answer is simple. We live in a bubble where it's small, because if we lived in a bubble where it was large, there'd be no galaxies, no stars, no planets, and no us. It's anthropic selection at work. The constant isn't small everywhere. It's small here, in our bubble, and that's why we're here to observe it. The same logic applies to other constants. The strength of gravity, the mass of the electron, the fine structure constant. All of them appear to be fine-tuned to allow for complex structures and life. And if you've only got one universe, that's a huge mystery. Why are all these constants set to just the right values? It seems like an incredible coincidence, or like something deliberately tuned them. But if you've got infinitely many universes with different constants, it's not a coincidence at all. It's inevitable. Somewhere in the infinite multiverse there's going to be a bubble with the right combination of constants, and we're in one of those bubbles because we couldn't be anywhere else. Now, before we go any further, I want to address the elephant in the room, because I know some of you are probably thinking, this sounds insane. How can we possibly take this seriously? We can't observe other bubbles. We can't test this. Isn't this just unfalsifiable philosophy dressed up as science? And that's a fair criticism. Eternal inflation does push the boundaries of what we traditionally think of as testable science. We can't directly observe other bubble universes because they're beyond our cosmic horizon, separated from us by eternally inflating space. We can't travel to them, we can't communicate with them, we can't even see light from them. So in that sense, they're completely inaccessible. But that doesn't mean eternal inflation is unfalsifiable. It makes predictions, just not the kind of predictions we're used to. For one thing, eternal inflation predicts that our universe should be infinite, or at least vastly larger than the observable universe, because that's the natural outcome of the inflationary process. And as we've discussed, observations of the universe's curvature are consistent with it being flat, which suggests it's infinite. That's a prediction of eternal inflation that's been confirmed. Eternal inflation also predicts certain patterns in the cosmic microwave background, the CMB. If our bubble universe nucleated within a larger inflating space, there might be subtle imprints of that process in the temperature fluctuations of the CMB. Specifically, if our bubble collided with another bubble at some point in the distant past, it would leave a distinctive signature, a kind of bruise in the CMB. Cosmologists have searched for these signatures, and so far they haven't found any convincing evidence. But the absence of evidence isn't evidence of absence. It could just mean that our bubble hasn't collided with another one, or that the collision happened so long ago that the signature has been stretched away by expansion. There's also the measure problem, which is one of the big challenges facing eternal inflation. If there are infinitely many bubbles, and each bubble is infinite in size, how do you calculate probabilities? How do you make predictions about what a typical observer should see? It's hard to compare infinities. If there are infinitely many observers in our bubble and infinitely many in other bubbles, which infinity is bigger? This is a real problem, and cosmologists have been working on it for decades. There are proposed solutions, different ways of defining what typical means in an infinite multiverse, but there's no consensus yet. It's one of the major open questions in the field. But the fact that eternal inflation raises these kinds of deep, difficult questions doesn't make it unscientific. It makes it frontier science. It's pushing the boundaries of what we can know, and yeah, that's uncomfortable. It forces us to rethink what it means to make a scientific prediction and what kinds of evidence we should consider. But that's how science progresses. You don't make breakthroughs by sticking to safe, easy questions. You make breakthroughs by venturing into the unknown and grappling with ideas that challenge your assumptions. And eternal inflation has earned its place at the table because it's not just wild speculation. It's a natural consequence of the inflationary model that's already incredibly successful at explaining the universe we observe. You don't have to add anything extra to inflation to get eternal inflation. It just falls out of the math if you take inflation seriously and follow the equations where they lead. That's a big deal. It means eternal inflation isn't some ad hoc idea cooked up to explain fine-tuning. It's a prediction of a theory that was developed to explain completely different problems, and the fact that it also addresses fine-tuning is a bonus. So let's recap where we are. Inflation, this period of exponential expansion in the first fraction of a second after the Big Bang, solves major problems in cosmology. But once you accept inflation, eternal inflation becomes almost inevitable. The inflation field doesn't decay everywhere at once. Some regions keep inflating while others stop, forming bubble universes. The inflating regions grow so fast that they dominate the total volume, and new bubbles keep forming within them forever. Our universe is one of those bubbles, and there are infinitely many others. And here's the kicker. Those other bubbles might have different physical constants. The laws of physics might vary from bubble to bubble, not because the underlying framework is different, but because the specific settings, the values of the constants, depend on how the inflaton field decayed in each bubble. Most bubbles are boring, sterile places where nothing interesting happens. But some bubbles, like ours, roll the dice and get a combination that allows for complexity, structure, and life. We're in one of those bubbles not because we're special, but because we couldn't be anywhere else. This has profound implications for how we think about our place in the cosmos. We've gone from thinking Earth is the center of the universe to realizing we're on an ordinary planet orbiting an ordinary star in an ordinary galaxy, and now eternal inflation is telling us that even our universe is ordinary. It's just one bubble among infinitely many, and there's nothing particularly special about it except that it's the one we happen to be in. It's the ultimate Copernican revolution, and it's humbling in the extreme. But it also raises a whole new set of questions. If there are infinitely many bubbles with different physical constants, what determines which constants are possible? Is there some underlying structure, some deeper theory that explains the range of possibilities? And if different bubbles have different laws, does that mean there's no such thing as a universal law of physics? Are the laws we've discovered just local bylaws, applicable only in our bubble? These are the questions that lead us into even stranger territory, into ideas about the multiverse that go beyond eternal inflation. Because eternal inflation gives us infinitely many bubble universes, but they're all part of the same overall structure, the same eternally inflating space. They all came from the same inflationary process, the same underlying physics. But what if there are other kinds of universes, other branches of reality that aren't connected to our inflationary background at all? What if the multiverse is even bigger, even more diverse than eternal inflation suggests? That's where we're headed next, into the full-blown multiverse hypothesis, the idea that reality isn't just one universe, or even infinitely many bubble universes, but a kaleidoscope of different kinds of universes, each with their own structure, their own rules, their own nature. Eternal inflation is just one piece of that larger picture, one way that a multiverse can arise, but there are others, and when you put them all together, you get a vision of reality that's so vast, so incomprehensible, that it makes everything we've talked about so far look like a warm-up act. So buckle up, because we're about to take this to the next level. So, eternal inflation gives us infinitely many bubble universes, each one a separate cosmos, potentially with different physical constants, different conditions, different histories. And if that wasn't mind-bending enough, if that wasn't already pushing the boundaries of what we can comprehend, well, buckle up, because we're about to go even deeper. Because eternal inflation is just one flavor of multiverse, one way that reality can be bigger and stranger than a single universe. But there are other kinds of multiverses, other ways that existence can multiply and branch and fragment into something so vast and so incomprehensible that it makes our heads spin. This is the full-blown multiverse hypothesis, and it's a kaleidoscope of different ideas, different theories, different frameworks, all pointing to the same unsettling conclusion: our universe isn't alone. Now, before we dive into the different types of multiverses, and trust me, there are several, we need to address something that's probably been nagging at you this entire time. Namely, how the hell can we possibly take any of this seriously? We've spent the last few chapters talking about regions of space we can never observe, bubble universes we can never visit, copies of ourselves living out different lives in unreachable corners of infinity. And now we're about to talk about entire categories of universes, whole frameworks of reality that exist beyond not just our cosmic horizon, but beyond anything we could ever hope to detect or measure. This sounds insane. It sounds like the kind of thing you'd come up with after spending too long staring at equations in a basement office at 3 in the morning, fueled by bad coffee and existential dread. And look, I get it. The multiverse hypothesis is controversial, even within the physics community. There are very smart, very respected physicists who think the whole idea is garbage, that it's not science because it's not testable, not falsifiable, not grounded in observation. They argue that if you can't observe something, if you can't make predictions that can be tested and confirmed or refuted, then it's not physics, it's philosophy at best and pseudoscience at worst. And that's a fair criticism. Science is supposed to be about evidence, about experiments, about making predictions and then checking whether nature agrees with you. If you're proposing the existence of things that can never be observed, never be tested, never leave any mark on our reality, then what exactly are you doing? Are you doing science, or are you just making stuff up? But here's the counter-argument, and it's one that I think deserves serious consideration. The multiverse isn't something that physicists just pulled out of thin air because they thought it would be cool or because they wanted to write best-selling pop science books. The multiverse, in all its various forms, arises naturally from theories that were developed to explain things we can observe. Inflation, for example, was developed to explain the uniformity of the cosmic microwave background and the flatness of the universe. Eternal inflation is a consequence of taking inflation seriously and following the math where it leads. Nobody set out to invent the multiverse. It emerged from the equations. And when your best theories, your most successful frameworks, keep pointing you toward the same conclusion, you can't just dismiss it because it makes you uncomfortable. Neil deGrasse Tyson, who's not exactly known for being a pushover when it comes to speculative physics, has said that he considers the multiverse a legitimate scientific hypothesis, not a theory, not an established fact, but a hypothesis worth taking seriously. And his reasoning is pretty straightforward. If you accept quantum mechanics, which is one of the most well-tested theories in all of physics, and if you accept general relativity, which is also extraordinarily well-tested, then certain versions of the multiverse follow naturally from combining those two frameworks. You don't have to add anything extra. You don't have to make wild assumptions. You just follow the math, and the multiverse is where it takes you. So with that context in mind, let's dive into the different types of multiverses. Now, there are a few different classification schemes out there, but the most widely used one is the system developed by the physicist Max Tegmark. Tegmark proposed 4 levels of multiverse, each one more abstract and more mind-bending than the last. These levels aren't mutually exclusive. You can have multiple levels operating at the same time, and in fact, most cosmologists who take the multiverse seriously think that's exactly what's going on. Reality is layered, with different kinds of multiverses stacked on top of each other, each adding its own flavor of weirdness to the mix. Let's start with level 1, which is actually the least strange of the bunch, if you can believe that. The level 1 multiverse is basically what we've already been talking about, the idea that our observable universe is just one region within a much larger, possibly infinite space. If the universe is infinite, or even just really, really big, and if the laws of physics are the same everywhere, then there are other regions out there, other Hubble volumes, other observable universe-sized bubbles, each with their own galaxies, their own stars, their own planets. And because there are only a finite number of ways to arrange particles within a given volume, those arrangements repeat. Somewhere out there, there's another Hubble volume that's identical to ours, with an identical Earth, an identical you, living an identical life. This isn't science fiction. This is a straightforward consequence of infinity plus physics. If space goes on forever and matter is distributed roughly uniformly, then every possible configuration of particles will occur somewhere, and it'll occur infinitely many times. Tegmark calculated that if the universe is infinite, there should be an identical copy of our entire observable universe about 10 to the power of 10 to the power of 115 meters away. That's a 1 followed by 10 billion trillion 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 zeros. It's a number so absurdly large that it doesn't even make sense to call it a number. But in an infinite universe, it's not just possible, it's guaranteed. Now this raises some seriously weird questions about identity and uniqueness. If there's another you out there, identical down to the last atom, living the exact same life, making the exact same choices, having the exact same thoughts, then in what sense are you unique? Is that other you actually you, or are they a different person who just happens to be identical? And if there are infinitely many copies of you, which one is the real you? These are the kinds of questions that keep philosophers up at night, and honestly, there's no easy answer. The level 1 multiverse doesn't care about our intuitions regarding identity. It just says, hey, if space is infinite and the laws of physics allow for a configuration like you, then that configuration exists infinitely many times. But it's not just identical copies. In an infinite universe, there are also near-identical copies, versions of you where one thing went differently. Maybe you chose a different career. Maybe you married a different person. Maybe you decided to have that extra cup of coffee this morning, and it set off a chain of events that led to a completely different day. All of those variations exist somewhere in the infinite expanse of space. Every possible version of you, every possible history, every possible choice, it's all out there, happening right now, in some distant Hubble volume that you'll never be able to observe or reach. This is profoundly unsettling, and it's also kind of unavoidable if the universe is infinite. The level 1 multiverse isn't something you can opt out of. It's just a consequence of the math. If space is infinite and homogeneous, then the level 1 multiverse exists. End of story. Now let's move on to level 2, which is where things start to get really interesting. The level 2 multiverse is what we get from eternal inflation, which we talked about in the last chapter. It's the idea that our universe is one bubble among infinitely many. Each bubble a separate pocket universe formed when the inflaton field decayed and inflation stopped in that region. But here's the key difference between level 1 and level 2. In level 2, the different universes don't all have the same physical constants. The laws of physics, or at least the settings, the parameters, can vary from bubble to bubble. In level 1, every Hubble volume operates under the same rules. Gravity has the same strength, the speed of light is the same, the mass of the electron is the same. The only thing that varies is the initial conditions, the specific arrangement of matter and energy. But in level 2, the rules themselves can be different. One bubble might have a cosmological constant that's 10 times larger than ours. Another might have a different mass for the electron. Another might have extra dimensions of space that are compactified in a different way. The possibilities are enormous, and each bubble is its own self-contained cosmos with its own unique properties. This is where the anthropic principle really comes into play. Most bubbles in the level 2 multiverse are going to be boring. They're going to have constants that don't allow for interesting structures. Maybe gravity is too strong and everything collapses immediately. Maybe the electromagnetic force is too weak and atoms can't form. Maybe the universe expands so fast that matter never clumps together. These bubbles are sterile wastelands, devoid of complexity, devoid of life. But some bubbles, by sheer chance, end up with a combination of constants that allows for galaxies and stars and planets and chemistry and, eventually, life. We're in one of those bubbles, not because there's anything special about us, but because we couldn't exist in any other kind of bubble. It's selection bias on a cosmic scale. The level 2 multiverse is controversial because it feels like a cop-out to some people. Instead of explaining why the constants have the values they do, it just says, well, they vary, and we happen to be in a place where they allow for life. But if eternal inflation is real, and the evidence strongly suggests it is, then the level 2 multiverse isn't a choice, it's a prediction. And it's a prediction that actually explains a lot, particularly the fine-tuning problem. Why is the cosmological constant so absurdly small? Because in most bubbles it's not, and those bubbles don't have observers. We're in a bubble where it's small because that's the only kind of bubble where we could exist to ask the question. Alright, so we've got level 1, the infinite repetition of configurations within an infinite space. We've got level 2, the bubble universes with varying physical constants from eternal inflation. Now let's talk about level 3, which is where things get genuinely bizarre, because level 3 is the quantum multiverse, also known as the many worlds interpretation of quantum mechanics. And if you thought eternal inflation was weird, just wait. Quantum mechanics is one of the most successful theories in the history of physics. It describes the behavior of particles at the smallest scales, and it's been tested to absurd levels of precision. Every prediction it makes gets confirmed over and over again. But there's a problem. Quantum mechanics tells us that particles don't have definite properties until you measure them. Before you measure a particle, it exists in a superposition, a state where it's simultaneously in multiple configurations at once. It's like Schrödinger's cat, the famous thought experiment. The cat is both alive and dead until you open the box and look. That's a superposition. But here's the thing. When you do open the box, you see one outcome. The cat is either alive or dead, not both. So what happened to the other possibility? Where did the superposition go? This is called the measurement problem, and it's one of the deepest mysteries in quantum mechanics. The standard interpretation, called the Copenhagen interpretation, says that the act of measurement causes the wave function to collapse. The superposition disappears, and you're left with one definite outcome. But that raises more questions than it answers. What counts as a measurement? Why does observation cause collapse? What's so special about conscious observers? The many worlds interpretation proposed by Hugh Everett in 1957 offers a radically different answer. It says there's no collapse. The wave function never collapses. Instead, every time a quantum measurement happens, every time a particle is in a superposition and could go one way or another, the universe splits. Both outcomes happen, but in separate branches of reality. The cat is alive in one branch and dead in another. You, the observer, split too. There's a version of you in one branch that sees the cat alive, and a version of you in another branch that sees the cat dead. Both versions are real, both branches exist. This is the level 3 multiverse, and it's happening constantly, all the time, everywhere. Every quantum event, every particle interaction, every moment where randomness enters the picture, the universe branches. The number of branches is staggering, incomprehensibly vast, and it's growing exponentially with every passing moment. Every possible outcome of every quantum event is realized in some branch. There's a branch where you decided to skip this video. There's a branch where you became an astronaut. There's a branch where you never existed because your parents never met. All of those branches are real, all of them exist, and all of them are equally valid. Now, here's where it gets really interesting. Tegmark has argued that the level 1 and level 3 multiverses are actually the same thing. They're two different ways of describing the same underlying reality. In an infinite level 1 multiverse, every possible configuration of particles exists somewhere. In the level 3 multiverse, every possible quantum outcome exists in some branch. But if you do the math, those two statements turn out to be equivalent. The infinite spatial repetition of level 1 and the infinite branching of level 3 are just different perspectives on the same multiverse. The many worlds interpretation is controversial, but it's also gaining traction, especially among younger physicists. A survey done a few years ago found that many worlds is now one of the most popular interpretations of quantum mechanics, rivaling the Copenhagen interpretation. And the reason is simple: it's clean. It doesn't require collapse. It doesn't require a special role for observers. It just says, take the math seriously, follow the equations, and don't add extra assumptions. The wave function is real, and all branches are real. It's a deeply unsettling idea, the notion that every time you make a choice, the universe splits, and both choices happen in separate branches. But it's also a natural consequence of taking quantum mechanics at face value. So we've got 3 levels now. Level 1, infinite space with repeating configurations. Level 2, bubble universes with varying physical laws. Level 3, quantum branching with every possible outcome realized. And now we come to level 4, which is the most abstract, the most philosophical, and frankly the most mind-bending of them all. Level 4 is the mathematical multiverse, and it's based on an idea proposed by Tegmark himself, called the mathematical universe hypothesis. Here's the basic idea. What if mathematics isn't just a tool we use to describe reality? What if mathematics is reality? What if every mathematical structure that's logically consistent corresponds to a real universe? Not a universe that's made of matter and energy, but a universe that is the mathematical structure itself. In this view, our universe is just one mathematical structure among infinitely many, and all of them exist in the same sense that we exist. The only reason we find ourselves in this particular structure is because it's one that allows for conscious observers, This sounds completely insane, but Tegmark has a pretty compelling argument for it. He points out that physicists have noticed for a long time that the laws of physics are mathematical, not just described by math, but fundamentally mathematical in nature. When you dig deep enough, when you strip away all the human interpretations and conceptual baggage, what you're left with are mathematical relationships. Space, time, particles, fields, all of them are ultimately just mathematical objects obeying mathematical rules. Tegmark takes this one step further and says, okay, if the universe is fundamentally mathematical, and if there's no aspect of reality that can't be described mathematically, then maybe the universe doesn't just have mathematical properties, maybe it is a mathematical structure. And if our universe is a mathematical structure, then why should it be the only one? Mathematics is full of structures. There are infinite kinds of geometries, infinite kinds of algebras, infinite kinds of logical systems. If one of those structures corresponds to a real universe, why not all of them? This is the Level 4 multiverse, the ultimate ensemble, where every mathematical structure that can exist does exist. Our universe, with its 3 spatial dimensions and 1 time dimension and its particular set of physical laws, is just one structure in an infinite library of mathematical realities. This is profoundly weird, and it raises questions that venture deep into philosophy. What does it even mean to exist in this context? If a mathematical structure exists in some abstract sense, does that count as the same kind of existence as you and me sitting here talking about it? Tegmark argues yes, that existence is a binary property. Either something exists or it doesn't, and there's no hierarchy of existence where some things are more real than others. If a mathematical structure is logically consistent, it exists, and any observers within that structure would perceive it as their reality. Critics of the Level 4 multiverse argue that it's untestable, unfalsifiable, and therefore not science, and they've got a point. How do you test the existence of other mathematical structures when you're embedded in one of them and can't access any of the others? Tegmark's response is that the mathematical universe hypothesis makes predictions. It predicts, for example, that our universe should be describable by a relatively simple mathematical structure, because complex structures are less likely to contain observers. It also predicts that we shouldn't observe any physical phenomena that can't be described mathematically, which, so far, we haven't. Every aspect of reality we've ever measured has turned out to be mathematical at its core. But even if you accept the Level 4 multiverse, it's a stretch. It requires you to accept a very particular philosophical stance about the nature of mathematics and existence, and not everyone is willing to go there. I'm not even sure I'm willing to go there, to be honest. But it's out there, it's been seriously proposed by a respected physicist, and it's part of the broader conversation about what the multiverse might look like. So let's take a step back and look at the full picture. We've got 4 levels of multiverse, each one adding a new layer of complexity and strangeness to reality. Level 1 says there are infinitely many regions of space like ours, with every possible configuration repeating infinitely. Level 2 says there are bubble universes with different physical constants carved out of an eternally inflating background. Level 3 says every quantum event creates branches, with all possible outcomes realized in parallel realities. Level 4 says every mathematical structure is a universe, and they all exist in some abstract sense. And here's the thing, these levels aren't mutually exclusive. You can have all of them at the same time. Our universe could be one bubble in a Level 2 multiverse, which is itself part of a Level 1 infinite space, and every quantum event within our bubble branches into a Level 3 multiverse, and all of that is just one mathematical structure in a Level 4 ensemble. It's multiverses all the way down, or all the way up, or all the way sideways, depending on how you want to think about it. Reality is a layered, fractal mess of infinite possibilities, and we're sitting in one tiny corner of it, trying to make sense of the whole thing. Now, what does all of this mean for probability and existence? If there are infinitely many universes, infinitely many versions of you, infinitely many realities, what does it even mean to say something is probable or improbable? In a level 1 multiverse, every configuration that can happen does happen infinitely many times, so the probability of any given configuration is both 0 and 100%, depending on how you define the sample space. In a level 3 multiverse, every quantum outcome happens in some branch, so nothing is truly random. Everything happens, just in different branches. This is the measure problem that cosmologists have been wrestling with for decades. How do you calculate probabilities in an infinite multiverse? How do you define what's typical or atypical when there are infinitely many of everything? It's a genuinely hard problem, and there's no consensus on the solution. Different cosmologists have proposed different measures, different ways of counting, different frameworks for making sense of infinity, but none of them are fully satisfying, and the debate is ongoing. There's also the question of what the multiverse means for our sense of identity and uniqueness. If there are infinitely many copies of you, are you still you? If every possible version of your life exists in some branch or some bubble or some distant Hubble volume, does your life have meaning? Does it matter what choices you make if some other version of you is making different choices in another branch? These are deep questions, and they don't have easy answers. Personally, I think the existence of other versions of me doesn't make my life any less meaningful. This version of me, the one sitting here right now, is the only version I have direct access to. The other versions are in branches I can't reach, bubbles I can't visit, regions of space I can't observe. For all practical purposes, they might as well not exist. My life, my choices, my experiences, they're mine, and they matter to me, regardless of whether there's another me somewhere else living a different life. But I get why the multiverse is unsettling. It challenges some of our deepest intuitions about reality, about identity, about what it means to be unique and special, and it forces us to confront the possibility that we're not unique or special at all, at least not in any cosmic sense. We're just one instance of a pattern that repeats infinitely across space, across quantum branches, across bubbles and mathematical structures. We're a blip, a single frame in an infinite film reel, and the universe doesn't care about us any more than it cares about any other blip. But here's the thing. Just because the universe doesn't care doesn't mean we can't care. Just because we're not cosmically unique doesn't mean our lives don't have value. The multiverse doesn't take anything away from us. It just puts things in perspective. It reminds us that we're part of something vastly larger than ourselves, something so big and so strange that we can barely wrap our heads around it. And there's a certain beauty in that, a certain awe-inspiring grandeur. We're tiny, insignificant, but we're also part of an infinite cosmos, part of a reality so vast and so complex that it boggles the mind. So where does all of this leave us? We've explored 4 different types of multiverse, each one arising from different branches of physics and cosmology. We've seen how infinity plus physics gives us level 1, how eternal inflation gives us level 2, how quantum mechanics gives us level 3, how mathematics and philosophy give us level 4, and we've seen that these levels can coexist, can stack on top of each other, creating a reality that's far stranger and far more layered than anyone ever imagined. But we're not done yet, because there's one more piece of the puzzle we need to talk about, one more framework that adds even more possibilities to the multiverse, and that framework is string theory, the ambitious attempt to unify all the forces of nature into a single mathematical structure. String theory doesn't just predict one universe or even infinitely many universes with varying constants. It predicts an almost unimaginable number of possible universes, something on the order of 10 to the power of 500 different vacuum states, each one corresponding to a different universe with different physical laws. This is the string landscape, and it's where the multiverse gets so complex, so vast, that even cosmologists who've been thinking about this stuff for decades start to feel dizzy. And that's exactly where we're headed next. String theory's playground, the 10 circumflex 500 universes. So we've established that the multiverse isn't just some wild speculation cooked up by bored physicists looking to sell books. It's a natural consequence of taking our best theories seriously and following them where they lead. We've got the level 1 multiverse from infinite space, the level 2 multiverse from eternal inflation, the level 3 multiverse from quantum mechanics, and even the level 4 multiverse from the mathematical universe hypothesis. Each layer adds its own flavor of strangeness, its own way of multiplying reality into something far vaster than we ever imagined. But there's one more piece of this puzzle we need to talk about. One more framework that doesn't just predict a multiverse, but predicts a multiverse so absurdly large, so incomprehensibly diverse, that it makes everything we've discussed so far look almost quaint by comparison. I'm talking about string theory, and specifically the string theory landscape. And when I say landscape, I'm not talking about a few dozen possible universes or even a few thousand. I'm talking about 10 to the power of 500 possible universes. That's a 1 followed by 500 zeros. And if you think that number is already hard to comprehend, just wait until we dive into what it actually means. Now, string theory is one of those topics that tends to either excite people or annoy the hell out of them, and there's really no in-between. For some people, string theory represents the pinnacle of human intellectual achievement, the most ambitious attempt in history to unify all the forces of nature into a single elegant mathematical framework. It's beautiful, it's deep, it's profound. For other people, string theory is the epitome of what's wrong with modern theoretical physics. It's untestable, it's unfalsifiable, it's a mathematical playground that's lost all connection to reality. It's been promising a revolution for decades and hasn't delivered. Both sides have a point, and we're going to try to navigate that minefield as we explore what string theory has to say about the multiverse. So let's start with the basics, because if you're going to understand the string landscape and why it leads to 10 to the power of 500 universes, you need to understand what string theory is and what problem it's trying to solve. The fundamental problem in modern physics is this. We've got two incredibly successful theories that describe how the universe works, but they don't play nicely together. On one hand, you've got general relativity, Einstein's theory of gravity, which describes how massive objects warp spacetime and how that warping creates what we perceive as gravitational force. General relativity works brilliantly on large scales. It predicts black holes, gravitational waves, the expansion of the universe, and every single one of those predictions has been confirmed by observations. It's one of the most successful theories in the history of science. On the other hand, you've got quantum mechanics and its extension, quantum field theory, which describes the behavior of particles at the smallest scales. Quantum field theory underlies the standard model of particle physics, which explains how all the fundamental particles interact via the electromagnetic force, the weak nuclear force, and the strong nuclear force. The standard model is also absurdly successful. It's made predictions that have been confirmed to 15 decimal places. It predicted the existence of particles like the Higgs boson decades before they were discovered. It's a triumph of human ingenuity. But here's the problem. General relativity and quantum mechanics are fundamentally incompatible. They're based on completely different mathematical frameworks, And when you try to combine them, when you try to apply quantum mechanics to gravity, the equations blow up. You get infinities, nonsensical answers, predictions that don't make sense. This has been a thorn in the side of physicists for nearly a century. We've got two theories that work perfectly in their own domains, but when you try to bring them together, they break. And there are situations where you absolutely need both theories. The center of a black hole, the first moments of the Big Bang. These are places where gravity is strong and quantum effects are important, and we don't have a consistent framework to describe what happens there. Enter string theory. The basic idea of string theory is both simple and utterly bizarre. Instead of thinking of particles as point-like objects with no size, no internal structure, just mathematical points, string theory says particles are actually tiny, one-dimensional loops or strands of energy. They're strings, hence the name. These strings are unimaginably small, on the order of the Planck length, which is about 10 to the power of -35 meters. That's a decimal point, followed by 34 zeros and then a 1. It's so small that if you scaled an atom up to the size of the solar system, a string would still be about the size of a tree. We're talking incomprehensibly tiny. But the key insight is this: these strings can vibrate. Just like a guitar string can vibrate in different modes, producing different musical notes, a fundamental string can vibrate in different patterns, and each vibration pattern corresponds to a different particle. One vibration mode gives you an electron, another gives you a quark, another gives you a photon. Every particle we've ever observed, every fundamental constituent of matter and energy, is just a different way that a string can vibrate. It's like the universe is a cosmic symphony, and all the different particles are different notes played by these tiny vibrating strings. Now, why does this solve the problem of combining quantum mechanics and gravity? Because in string theory, the graviton, the hypothetical particle that mediates the gravitational force, naturally falls out of the equations. It's one of the vibration modes of the string. You don't have to add gravity in by hand, it's already there, baked into the framework. And because strings have a finite size, even if that size is unimaginably small, they smooth out the infinities that plague attempts to quantize gravity using point particles. The mathematical inconsistencies that broke quantum gravity with point particles don't show up when you use strings instead. It's elegant, it's beautiful, and it potentially solves one of the biggest problems in physics. But, and this is a huge but, string theory comes with some seriously weird baggage. The most famous piece of baggage is this: for the math to work, for the equations to be consistent, strings can't exist in the four-dimensional space-time we're familiar with, 3 dimensions of space and 1 dimension of time. No, strings need 10 dimensions, 9 dimensions of space plus 1 dimension of time. That's what the equations demand. If you try to do string theory in 4 dimensions, the math doesn't work. You get inconsistencies, anomalies, things that don't make sense, but in 10 dimensions, everything clicks into place. The equations are beautiful, they're consistent, they're mathematically rigorous. Now obviously we don't see 10 dimensions, we see 3 dimensions of space. Up, down, left, right, forward, backward. That's it. So where are the other 6 spatial dimensions hiding? The answer, according to string theory, is that they're compactified. They're curled up so small that we can't perceive them. Imagine you're an ant walking on a tightrope. From your perspective, the tightrope is a one-dimensional line. You can move forward or backward, and that's it. But if you were really, really tiny, you'd realize that the tightrope actually has another dimension. It has a thickness, a circumference. You could walk around the tightrope in a circle. That circular dimension is always there. But if you're big relative to the tightrope, you don't notice it. String theory says the same thing is happening with the extra 6 dimensions. They're there, they exist. but they're curled up into shapes so tiny on the scale of the Planck length that we can't detect them. From our perspective, space looks three-dimensional, but if you could zoom in far enough, you'd see that at every point in space, there are 6 additional dimensions curled up into some complicated geometric structure. These structures are called Calabi-Yau manifolds, and they're some of the most complex and beautiful objects in all of mathematics. Now, here's where things get interesting, because there's not just one way to curl up 6 dimensions, there are many, many ways. In fact, there are an absolutely staggering number of ways. Early estimates suggested there might be thousands or millions of possible Calabi-Yau shapes. But as mathematicians and physicists dug deeper, as they explored the full space of possibilities, they realized the number was far, far larger. Current estimates put the number of possible compactifications, the number of different ways you can curl up the extra 6 dimensions, at around 10 to the power of 500. That's the string landscape, and each one of those 10 to the power of 500 compactifications corresponds to a different universe with different physical laws. Let me say that again because it's important. 10 to the power of 500. That's not a typo, that's not hyperbole. That's the actual estimate for the number of distinct ways the extra dimensions can be configured. And each configuration gives you a different set of physical constants: the mass of the electron, the strength of gravity, the value of the cosmological constant. All of these depend on how the extra dimensions are curled up. Change the shape and you change the physics. It's like each Calabi-Yau manifold is a different tuning knob for the universe, and there are 10 to the power of 500 different settings. Now, to put this number in perspective, let's try to comprehend just how absurdly large 10 to the power of 500 is. The number of atoms in the observable universe is estimated to be around 10 to the power of 80. That's a 1 followed by 80 zeros. That's already an incomprehensibly large number, but 10 to the power of 500 is 1 followed by 500 zeros. If you wanted to write out this number in full, if you used every atom in the observable universe as a single digit, you'd run out of atoms long before you finished writing the number. You'd need 10 to the power of 420 more universes worth of atoms just to write it down. This is a number that defies comprehension. It's larger than anything we've ever encountered in any practical context, and it represents the number of possible universes in the string landscape. Each one of those 10 to the power of 500 configurations is technically possible according to string theory. Each one is a valid solution to the equations, and in each one, the laws of physics are different. Some of them might look vaguely like our universe, with similar constants and similar particles, but the vast, vast majority of them are going to be completely alien. Universes where electrons are 1,000 times heavier, universes where gravity is 1,000,000,000 times stronger, universes where there are extra forces we've never imagined, universes where the cosmological constant is so large that space tears itself apart instantly. The diversity is incomprehensible, and our universe is just one point in this vast landscape of possibilities. Now, when string theorists first started realizing the size of the landscape, there was a bit of a crisis. See, one of the appeals of string theory was that it was supposed to be a unique theory. The hope was that once you worked out all the details, string theory would give you one and only one consistent universe, and that universe would be ours. The constants would be determined by the theory itself. You wouldn't need to measure them, you'd calculate them from first principles. It was supposed to be the ultimate unification, the theory of everything that explained why the universe is the way it is. But the landscape shattered that dream. Instead of one unique universe, string theory gave physicists 10 to the power of 500 universes. Instead of predicting the constants, it gave them a menu of options and no clear way to choose which one is correct. This was, to put it mildly, a huge disappointment. It meant that string theory couldn't make definitive predictions about our universe. It couldn't tell you why the electron has the mass it does, or why the cosmological constant is so small. All it could say is that somewhere in the landscape there's a configuration that matches our universe, but good luck finding it among 10 to the power of 500 possibilities. Some physicists saw this as a fatal flaw. If string theory can't make unique predictions, if it can accommodate essentially any universe, then what's the point? It's unfalsifiable, you can't test it. And if you can't test it, it's not science. This criticism has been leveled at string theory for decades, and it's one of the main reasons the theory has become so controversial. There are very smart, very respected physicists who think string theory is a dead end, a beautiful mathematical structure that has no connection to reality. But other physicists took a different view. They said, okay, maybe string theory doesn't give us one unique universe, but what if that's not a problem? What if the landscape is real? What if all 10 to the power of 500 configurations actually exist somewhere? This is where the string landscape connects to the multiverse. If eternal inflation is real and it creates infinitely many bubble universes, and if string theory is the correct description of fundamental physics, then each bubble could land on a different point in the string landscape. Each bubble could have a different compactification, a different set of physical laws. The landscape isn't a bug, it's a feature. It's telling us that the multiverse is real, and it's far more diverse than we ever imagined. This idea was championed by physicists like Leonard Susskind, who literally wrote the book on the string landscape. Susskind argued that the landscape, combined with eternal inflation, is the answer to the fine-tuning problem. Why is the cosmological constant so small? Why are the constants of nature set to values that allow for life? Because somewhere in the landscape, there's a configuration that has those values, and we're in one of those bubbles because we couldn't exist in any other kind. It's the anthropic principle all over again, but now it's backed by an actual theory, string theory, that predicts the existence of 10 to the power of 500 different universes. Now, to understand how the landscape works, we need to talk a bit more about the technical details, and I promise I'll keep this as non-technical as possible. In string theory, the properties of the universe, the particles, the forces, the constants, are all determined by something called the vacuum state. The vacuum state is the lowest energy configuration of the string fields. It's what the universe settles into once all the high-energy dynamics have calmed down. And the vacuum state, in turn, is determined by how the extra dimensions are compactified. Think of it like a ball sitting in a landscape of hills and valleys. The ball represents the state of the universe, and it wants to roll downhill to the lowest point, the minimum energy. The shape of the landscape, the locations of the valleys, are determined by the geometry of the extra dimensions. Each valley corresponds to a different vacuum state, a different set of physical laws. The string landscape has 10 to the power of 500 valleys, and the ball can end up in any one of them. Most valleys are high up, corresponding to universes with very high energy, very different physics, and they're unstable. But some valleys are low and stable, and those are the universes that can last long enough for interesting things to happen. Our universe is in one of those low, stable valleys. The cosmological constant, the thing that's causing the universe's expansion to accelerate, corresponds to the energy of the vacuum we're in. It's small, but it's not zero, which means we're in a valley that's just barely above the absolute minimum, and that's consistent with what we observe. The cosmological constant in our universe is about 10 to the power of negative 120 in Planck units, which is absurdly small but not quite zero. String theory says that somewhere in the landscape there's a valley with exactly that energy, and that's where we are. But here's the thing. We don't know how to calculate which valley corresponds to our universe. The math is just too hard. Calabi-Yau manifolds are incredibly complex geometric objects, and figuring out the exact properties of each compactification is a monumental task. Physicists have been able to study a few specific examples in detail, but we're nowhere close to mapping out the entire landscape. We don't know which of those 10 to the power of 500 configurations is ours. We just know it's in there somewhere. This has led to a fascinating development in string theory called the swampland program. The idea is to figure out which configurations are actually consistent and which ones are not. Just because you can write down a compactification doesn't mean it's physically viable. There might be subtle inconsistencies, things that look fine at first but break down when you dig deeper. The swampland program, pioneered by physicist Cumrun Vafa in the mid-2000s, is an attempt to rule out large swaths of the landscape by identifying these inconsistencies. If you can narrow down the possibilities, if you can say that certain regions of the landscape are in the swampland and can't correspond to real universes, then maybe you can make progress toward finding where our universe sits. And there's been some success here. The swampland program has identified certain conjectures, certain rules that seem to apply across all of string theory, and some of these conjectures have been tested against observational data. For example, one of the swampland conjectures has implications for inflation, and it turns out that data from experiments like BICEP2, which studied the cosmic microwave background, are consistent with the swampland predictions. It's not a smoking gun, but it's a hint that string theory and the landscape might be on the right track. Now, let's talk about the history of string theory for a second, because it's a wild ride. String theory didn't start out as a theory of quantum gravity. It started in the late 1960s as an attempt to understand the strong nuclear force, the force that holds quarks together inside protons and neutrons. Physicists were studying something called scattering amplitudes, and they found that these amplitudes could be explained by modeling particles as tiny vibrating strings. It was a bizarre idea, but it worked, at least for a little while. But then quantum chromodynamics, QCD, came along and provided a much better explanation for the strong force, and string theory as a theory of strong interactions was abandoned. It looked like string theory was dead. But then, in the mid-1970s, physicists realized something remarkable. One of the vibration modes of the string corresponded to a massless spin-2 particle, and there's only one particle in nature that fits that description, the graviton, the hypothetical quantum of gravity. String theory wasn't a theory of the strong force. It was a theory of everything, including gravity. This realization kicked off what's called the first superstring revolution in the early 1980s. Physicists developed 5 different versions of string theory, each with its own mathematical structure, and they showed that all 5 were mathematically consistent and anomaly-free. This was a huge deal, because prior attempts to quantize gravity had always run into problems. But string theory worked. The infinities disappeared, the equations made sense, and for the first time, physicists had a viable candidate for a theory of quantum gravity. But there was a problem. Why 5 theories? If string theory is supposed to be the ultimate unified theory, there should only be one version, not 5. This puzzle lingered for over a decade, until the mid-1990s, when physicists realized that all 5 string theories, plus an additional framework called 11-dimensional supergravity, were actually different limits of a single, more fundamental theory. They called this theory M theory. Nobody's entirely sure what the M stands for. Some say it's for membrane, because M theory includes higher dimensional objects called branes. Others say it's for mystery, because M theory is still not fully understood. Either way, M-theory unified the five string theories and suggested that the fundamental structure might actually be 11-dimensional, not 10. This was the second superstring revolution, and it brought renewed excitement to the field. But it also brought the landscape. As physicists explored the implications of M-theory and string theory more deeply, they realized just how many compactifications were possible, and the number kept growing. By the early 2000s, it was clear that the landscape was enormous, and the dream of a unique predictive theory was fading. Now, one of the major successes of string theory, and something that gave the field a lot of credibility, happened in 1996. Physicists Andrew Strominger and Kamran Vafa used string theory to calculate the entropy of a certain type of black hole, and they got the exact answer that Stephen Hawking had derived years earlier using semi-classical methods. This was the first time anyone had been able to derive black hole entropy from a fundamental quantum theory, and it was a huge win for string theory. It showed that string theory wasn't just abstract math. It could connect to real physical phenomena, and it could give you the right answers. But despite successes like that, string theory has struggled to make contact with experiment. The energies required to directly probe the Planck scale where strings live are far, far beyond anything we can achieve with particle accelerators. You'd need an accelerator the size of the galaxy to reach those energies, and that's obviously not happening anytime soon. So string theorists have been searching for indirect tests, ways that string theory might leave an imprint on phenomena we can observe. The swampland program is one approach. Another is looking for signatures of extra dimensions in high-energy particle collisions or in gravitational waves. But so far, nothing definitive has turned up. This has led to a lot of frustration, both within the string theory community and outside it. Critics argue that if a theory can't be tested, it's not science, it's math, it's philosophy, but it's not physics. And they have a point. Science is supposed to be about making predictions and testing them against reality. If string theory can accommodate essentially any observation because of the enormous landscape, then what predictive power does it have? How do you falsify it? String theorists counter that the lack of experimental tests doesn't mean the theory is wrong or useless. It just means we're working at the frontier of knowledge, in a regime where experiments are incredibly difficult. And they point out that string theory has made theoretical progress on problems that seemed intractable, like black hole entropy and the unification of forces. It's given physicists new mathematical tools, new ways of thinking about quantum field theory and gravity. Even if we can't test it directly, it's been immensely valuable as a theoretical framework. But the landscape, with its 10 to the power of 500 universes, remains one of the most controversial aspects of string theory. It's forced physicists to grapple with questions about the nature of scientific explanation. What does it mean to explain something if your theory gives you 10 to the power of 500 possible answers? Is that even an explanation? Or is it just saying, well, anything goes and we happen to be in one of the configurations that allows for observers? Some physicists have embraced this. They've said, okay, maybe the job of physics isn't to explain why the constants have the values they do. Maybe the job is to identify the space of possibilities and understand the selection mechanisms, like eternal inflation and the anthropic principle, that determine which possibilities are realized and which ones we can observe. It's a shift in perspective, a move away from determinism and uniqueness toward a more probabilistic, landscape-based view of reality. Other physicists hate this. They see it as giving up on the original goal of physics, which is to find a unique, elegant theory that explains everything from first principles. They argue that if you accept the landscape and the anthropic principle, you're abandoning the search for deeper understanding. You're saying, we can't explain the constants, so we'll just invoke a multiverse and say they vary. To critics, this feels like a cop-out, like intellectual surrender. But here's the thing, nature doesn't care what we think is elegant or satisfying. If the landscape is real, if string theory is correct, and there really are 10 to the power of 500 possible configurations, then that's just how reality is. We don't get to choose. We have to follow the evidence and the mathematics, even if it leads us to conclusions that make us uncomfortable. And the evidence from cosmology, from inflation, from the fine-tuning of the constants, all of it points in the same direction. It points toward a multiverse, a vast ensemble of universes with different properties. String theory gives us a concrete realization of that idea, a framework where the multiverse isn't just speculation but a prediction. And that brings us to the edge of something even deeper, something even more unsettling. Because if there are 10 to the power of 500 universes in the string landscape, each with different laws, different particles, different constants, then we're forced to confront a question that goes beyond physics and cosmology and ventures into pure philosophy. What does it mean for something to exist? If a universe is mathematically consistent but contains no observers, does it exist in the same sense that our universe does? And if most of the landscape is sterile, empty, devoid of life and consciousness, then what does that say about the nature of existence itself? These are questions that don't have easy answers, and they're questions that physics alone can't resolve. They require us to think about the meaning of reality, the role of observers, the relationship between mathematics and existence, and that's exactly where we're headed in the final chapter. Because once you've accepted the multiverse, once you've accepted that there might be 10 to the power of 500 universes, or infinitely many universes, you're left with one last terrifying question. What does it mean for there to be nothing? What is the true nature of reality itself, and is there any such thing as an ultimate final answer? These are the questions that keep cosmologists and philosophers awake at night, and they're the questions we're going to tackle as we wrap up this journey into the edge of the universe and beyond. The true meaning of nothing, the enigma of reality itself. Alright, so we've spent the last 6 chapters building up this impossibly vast picture of reality. We've talked about the cosmic horizon, this boundary we can never cross because light hasn't had time to reach us. We've talked about how the universe doesn't have a center, how every observer sits in the middle of their own bubble. We've talked about the universe extending far beyond what we can see, possibly infinitely. We've talked about eternal inflation, creating infinitely many bubble universes, each one a separate cosmos. We've talked about the multiverse hypothesis, this kaleidoscope of different types of multiverses stacked on top of each other. And we just finished talking about string theory and the landscape, 10 to the power of 500 possible universes, each with different laws of physics. And if your head isn't spinning at this point, if you're not feeling at least a little bit existentially overwhelmed, then you probably haven't been paying attention. Because what we've been building up to, what all of this has been pointing toward, is a question so fundamental, so deep, that it sits at the very foundation of everything we've been discussing. And that question is this: what the hell is nothing? Now, I know that sounds like a stupid question. You know what nothing is, right? Nothing is the absence of something. It's empty space. It's a void. It's what you get when you take everything away. If I've got a box and I remove everything from it, all the air, all the particles, all the radiation, then what's left is nothing. Easy, obvious. Except here's the thing, that's not nothing. That's really, really not nothing. And the more you think about it, the more you dig into what nothing actually means, the weirder and more unsettling it gets. Because it turns out that nothing, true nothing, the kind of nothing you're probably imagining when you hear the word, might be completely impossible. And if true nothing is impossible, then reality itself is far stranger and far more inevitable than we ever imagined. So let's start by breaking down what we usually mean when we say nothing, because this is where most people's intuitions completely fall apart. When you think of empty space, when you picture a perfect vacuum, what are you imagining? Probably a region of space where there's no matter, no particles, no stuff. It's just empty. But here's the problem. Empty space isn't empty, not even close. Even if you could somehow remove every single particle from a region of space, even if you could create a perfect vacuum where there's absolutely no matter or radiation, that space would still be seething with activity on the quantum level. This is where quantum mechanics comes in and completely destroys our everyday intuitions about what empty space looks like. See, quantum mechanics has this thing called the Heisenberg uncertainty principle, which was formulated way back in 1927 by Werner Heisenberg. The uncertainty principle tells us that there are certain pairs of properties that you can't know precisely at the same time. The more accurately you know one, the less accurately you can know the other. The most famous example is position and momentum. If you know exactly where a particle is, you can't know how fast it's moving, and vice versa. But there's another pair of properties that the uncertainty principle applies to, and it's even weirder: energy and time. The uncertainty principle says that if you look at a very short time interval, the energy during that interval can fluctuate wildly, and I mean wildly. Over short enough timescales, energy can appear out of nowhere, violate conservation of energy, and then disappear again before anyone notices. It's like the universe is playing a shell game with energy, and as long as it puts the energy back before the cosmic accountant checks the books, it can get away with it. And this isn't just theoretical speculation. This happens all the time, everywhere. Right now, in the supposedly empty space between you and your screen, the vacuum is fluctuating with energy. Particle-antiparticle pairs are popping into existence, existing for a tiny fraction of a second and then annihilating each other and disappearing back into the void. These are called virtual particles, and they're a fundamental feature of quantum field theory. The vacuum isn't empty. It's a roiling foam of particles constantly appearing and disappearing, a quantum ocean of activity that we can't see but that has real, measurable effects. One of the most famous demonstrations of virtual particles is something called the Casimir effect, which was predicted in 1948 by the Dutch physicist Hendrik Casimir and experimentally confirmed in 1997. Here's how it works. Take two metal plates and put them really, really close together in a vacuum. Now, you'd think that if the vacuum is truly empty, there should be no force between the plates, but that's not what happens. The plates are attracted to each other. They're pulled together by a tiny but measurable force. Why? Because of virtual particles. In the space between the plates, only certain wavelengths of virtual particles can exist. The plates are like walls, and they restrict which quantum fluctuations can happen between them. But outside the plates, in the open vacuum, all wavelengths are allowed. So there are more virtual particles pushing on the outside of the plates than on the inside, and that imbalance creates a net force pulling the plates together. It's a tiny force, but it's real, it's been measured, and it's direct evidence that the vacuum isn't empty. It's full of quantum activity. So the average energy density of the vacuum, this seething ocean of virtual particles, is estimated to be around 10 to the power of -9 joules per cubic meter. That's a small number, but it's not zero. The vacuum has energy. And if the vacuum has energy, then it's not nothing, it's something. It's a quantum field in its lowest energy state, but that lowest energy state still has structure, still has properties, still has stuff happening. This idea of quantum foam was popularized by the physicist John Wheeler back in 1955. Wheeler realized that at the smallest scales, at the Planck scale, which is about 10 to the power of negative 35 meters, space-time itself should be fluctuating, not just particles and energy, but the very fabric of space and time should be frothing and bubbling due to quantum effects. At that scale, space-time doesn't look smooth. It looks like a turbulent foam with tiny wormholes and black holes and all kinds of bizarre structures constantly appearing and disappearing. We can't observe this directly because the Planck scale is so incomprehensibly small, but the math of quantum gravity suggests it's there. Virtual particles also play a role in one of the most famous phenomena in theoretical physics, Hawking radiation. Back in 1974, Stephen Hawking showed that black holes aren't actually completely black. They emit radiation due to quantum effects near the event horizon. Here's the basic idea. Virtual particle-antiparticle pairs are constantly popping into existence everywhere, including right at the edge of a black hole. Normally, these pairs annihilate each other almost instantly. But if one of the particles falls into the black hole while the other escapes, the escaping particle becomes real. It carries energy away from the black hole, and over time the black hole loses mass and eventually evaporates. This is Hawking radiation, and it's a direct consequence of the fact that the vacuum isn't empty. It's full of virtual particles that can become real under the right circumstances. So when physicists talk about empty space, when they talk about the vacuum, they're not talking about nothing. They're talking about a quantum field in its ground state, a state that's full of fluctuations and activity. True nothing, the kind of nothing where there's absolutely no structure, no fields, no quantum fluctuations, no anything. That's not what the vacuum is. The vacuum is something. It's a very specific kind of something with very specific properties. But okay, let's take this a step further. Let's say you're not satisfied with calling the vacuum something. You want to go deeper. You want to strip away the quantum fields, strip away space-time itself, and ask, what's left? What was there before the Big Bang, before space and time existed? Was there true nothing then? This is where we get into some seriously deep philosophical and cosmological territory, because different physicists and philosophers have different answers to this question. Let's start with the cosmologist Lawrence Krauss, who wrote a book in 2012 called A Universe from Nothing. Krauss's argument, and it's one that generated a ton of controversy, is that the universe could have arisen from a quantum vacuum fluctuation. The idea is that the vacuum, even though it has energy and structure, is unstable. It can spontaneously create universes. Here's the basic idea. The total energy of the universe might be zero. You've got positive energy in the form of matter and radiation, but you've also got negative energy in the form of gravity. Gravitational potential energy is negative, and if you add up all the positive energy and all the negative energy in the universe, they might exactly cancel out. The universe might be a free lunch, energetically speaking. And if the total energy is zero, then creating a universe doesn't violate conservation of energy. You're not creating something from nothing. You're creating a system where the books balance, where the total adds up to zero. Krauss goes further and argues that in quantum mechanics, anything that can happen will happen given enough time. If the vacuum can fluctuate and create a tiny universe-sized bubble with zero total energy, then eventually it will. The probability might be incredibly small, but over infinite time it's inevitable. And once that bubble is created, it can undergo inflation, expand exponentially, and become a full-fledged universe like ours. In Krauss's view, the universe is the ultimate quantum fluctuation, a random blip in the vacuum that happened to inflate and create everything we see. Now, Krauss got a lot of criticism for this book, and a lot of that criticism was justified. Philosophers in particular were not happy. because they argued that Krauss was playing fast and loose with the word nothing. When Krauss says the universe came from nothing, what he really means is it came from a quantum vacuum, a state that has fields and laws and structure. That's not nothing in the philosophical sense, that's something. True nothing would be the absence of quantum fields, the absence of physical laws, the absence of space-time itself. And Krauss doesn't really address that. He just redefines nothing to mean the quantum vacuum, and then says, see, the universe came from nothing. Philosophers like David Albert absolutely tore into Krauss for this. Albert pointed out that if you've got quantum fields and laws of physics, then you've already got something, and the question just gets pushed back one level. Where did the quantum fields come from? Where did the laws come from? Why is there a quantum vacuum instead of true nothing? Krauss's response was basically, look, as a physicist, I deal with what the physics tells me. The physics says the vacuum can create universes, so that's what I'm saying. The deeper philosophical question of why there's anything at all, why there are laws, why there's a framework for reality, that's not a question physics can answer. And maybe it's not a question that has an answer. But there are other physicists who've tried to address that deeper question. Alexander Vilenkin, who we've talked about before in the context of eternal inflation, proposed a model in 1982 where the universe literally tunnels into existence from nothing. And by nothing, Vilenkin means something closer to the philosophical sense. No space, no time, no fields. Vilenkin's model uses quantum tunneling, the idea that in quantum mechanics, particles can pass through barriers that they classically shouldn't be able to cross. Vilenkin applies this idea to the universe itself. He says the universe can tunnel from a state of no space and no time into a state where space-time exists. It's a bizarre idea, and it's hard to wrap your head around because we're so used to thinking of causation as something that happens in time. Event A causes event B, and A comes before B. But if there's no time before the Big Bang, then there's no before. Causation doesn't work the way we're used to. The universe doesn't come from anything in the usual sense. It just is. It exists as a quantum fluctuation, a tunneling event from a state that has no temporal or spatial structure. This idea ties into something called the Hartle-Hawking no-boundary proposal, which was developed by James Hartle and Stephen Hawking in 1983. The no-boundary proposal is an attempt to describe the origin of the universe using quantum cosmology. The basic idea is that the universe doesn't have a boundary in time. If you go back far enough, time itself becomes fuzzy and ill-defined due to quantum effects. Hawking talks about imaginary time, which is a mathematical trick, where time becomes another dimension of space. In this framework, the question of what came before the Big Bang doesn't make sense because there is no before. Time doesn't extend infinitely into the past. It just starts, smoothly, without a sharp boundary or a moment of creation. Hawking once said, asking what came before the Big Bang is like asking what's north of the North Pole. It's a meaningless question because you can't go further north than the North Pole. Similarly, you can't go further back in time than the Big Bang because time itself begins there. There's no before, there's no prior state, the universe just is. Now this is where we start to venture into what some people call meta-nothing, the idea of a state that lacks not just matter and energy, but space, time, and physical laws. This is the kind of nothing that philosophers have been grappling with for millennia. The question, why is there something rather than nothing, was famously posed by the philosopher Gottfried Wilhelm Leibniz back in 1714, and it's been echoed by thinkers throughout history. Martin Heidegger, the German philosopher, called it the fundamental question of metaphysics in 1929. It's the ultimate mystery, the deepest question you can ask. And modern physics doesn't really have a satisfying answer. Vilenkin has said that nothing is unstable. He argues that the state of true nothing, no space, no time, no laws, is so ill-defined that it's unstable. Quantum mechanics, or something like it, might exist even in the absence of space-time, and that framework allows for the spontaneous creation of universes. In this view, nothing is impossible because the rules of quantum mechanics won't let it exist. The moment you have any kind of framework, any kind of structure, even the bare-bones structure of quantum rules, you've already got something, and that something can create more something. But here's where it gets really unsettling. If nothing is impossible, if reality is inevitable, then existence itself is brute fact. There's no deeper explanation. Reality exists because it has to. It's a logical necessity, not a contingent accident. And that's terrifying in its own way, because it means we can't point to some prior cause, or some external creator, or some reason why things are the way they are. They just are. Reality is self-explanatory, or perhaps it's not explanatory at all. It just exists, and we're stuck in it, trying to make sense of it. This brings us back to that question from Parmenides, the ancient Greek philosopher from around 500 BCE. Parmenides famously said, "Nothing comes from nothing." He argued that if there was ever a state of absolute nothing, then there would still be nothing now, because nothing can't give rise to something. It's a logical argument, and for centuries it seemed airtight. But modern physics suggests Parmenides was wrong, or at least that his concept of nothing was too simplistic. Quantum mechanics says that nothing, in the sense of the quantum vacuum, is unstable. It can and does give rise to something. Virtual particles, universes, entire multiverses, all of it can emerge from the quantum foam. But again, the vacuum isn't true nothing, it's something. So maybe Parmenides was right in a deeper sense. Maybe true nothing, the kind of nothing that has no structure, no laws, no potential, is impossible, and that's why there's something. The universe exists because the alternative, true nothing, can't exist. It's logically or physically incoherent. Now, let's talk about one of the most terrifying implications of all this, because we're not just dealing with abstract philosophy here. We're dealing with real physics that has real consequences, and one of those consequences is something called vacuum decay. Remember when we talked about the string landscape and how different regions of the landscape correspond to different vacuum states with different physical laws? Well, the vacuum we're in right now, the one that determines the laws of physics in our universe, might not be the lowest energy state. It might be a false vacuum. A false vacuum is a state that looks stable, that seems like it's at the bottom of the energy well, but actually there's a lower state available. It's like a ball sitting in a shallow valley on the side of a mountain. The ball is stable for now, but if you give it a little push, it'll roll down to a deeper valley at a lower elevation. The question is, could our universe be sitting in a false vacuum? And if so, what happens if it decays to the true vacuum? The physicist Sidney Coleman worked this out back in 1977 and 1980. Coleman showed that if we're in a false vacuum, then at some random point, somewhere in the universe, a bubble of true vacuum will nucleate. Inside that bubble, the laws of physics are different. The constants have different values, and the bubble expands at the speed of light. It's a sphere of destruction, racing outward, converting everything it touches into a new kind of universe with new laws. And there's no warning. You wouldn't see it coming because it's moving at light speed. One moment, everything is fine. The next moment, you've been converted into different physics and you're gone. Now, the good news is that the time scale for this kind of vacuum decay is probably incredibly long, on the order of 10 to the power of 20 years or more, depending on the specifics of the vacuum we're in. That's far longer than the current age of the universe. The probability of it happening anytime soon is vanishingly small, but it's not zero. It could happen tomorrow, It could happen in 1 trillion years. We don't know, and there's nothing we can do about it. If vacuum decay is possible, then it's just a ticking time bomb built into the fabric of reality. This ties into a broader point about the instability of nothing and the fragility of the laws of physics. We tend to think of the laws of nature as fixed, eternal, unchanging. Gravity has always been gravity. The speed of light has always been the speed of light. But if we're in a false vacuum, if the string landscape is real, and there are 10 to the power of 500 other vacuum states out there, then the laws we observe are just local bylaws, temporary features of our particular bubble. They're not fundamental, they're contingent, and they could change. This is a deeply unsettling realization. It means that the universe we know, the one we've spent centuries studying and trying to understand, is not as stable or as permanent as we thought. It's a temporary configuration, a metastable state that could transition to something else at any moment, and that transition would be catastrophic. Everything we know, everything we are, would be erased, replaced by a different universe with different rules. Alan Guth, the physicist who proposed cosmic inflation back in 1980, once described the universe as the ultimate free lunch. His point was that if the total energy of the universe is zero, then creating a universe costs nothing. It's free. And if it's free, then there's no reason it can't happen over and over again, infinitely many times, creating the multiverse we've been talking about. But Guth's free lunch comes with a price. If universes can be created from nothing, if the vacuum is unstable and eternally inflating, then the process never stops. New bubbles, new universes, new realities are being created all the time, and they'll continue to be created forever. This is eternal inflation, the idea we talked about in Chapter 4. Andre Linde developed this framework in the mid-1980s, and it's become one of the leading models in cosmology. Eternal inflation says that once inflation starts, it never fully stops. Some regions decay and form pocket universes, but other regions keep inflating, and new pockets keep forming. The multiverse is eternal, constantly growing, constantly branching, infinitely creative. But it also means that nothing is truly fundamental. There's no ultimate ground state, no final answer. Reality is an eternal, self-perpetuating process, a cosmic engine that just keeps running, creating more and more structure, more and more complexity, with no end in sight. And we're just one tiny byproduct of that process, one bubble among infinitely many, existing for a brief moment before the cosmic machinery moves on. So what does all of this tell us about nothing? What have we learnt from this deep dive into quantum mechanics, cosmology, and philosophy? The answer, I think, is that nothing, in the sense that most people understand it, doesn't exist. True nothing, a state with no space, no time, no fields, no laws, no potential, is either impossible or so unstable that it can't last. The moment you have any kind of framework, any kind of rules, you've already got something, and that something can create more something. The vacuum isn't empty. Space-time isn't inert. The universe isn't static. Everything, at every level, is dynamic, fluctuating, changing. Nothing is always becoming something, and maybe that's the ultimate answer to Leibniz's question, why is there something rather than nothing? Because nothing is impossible. Reality exists because it has to, because the alternative is incoherent, unstable, or simply undefined. But here's the really terrifying part, the part that keeps cosmologists and philosophers up at night. We have no reason to believe that reality has any obligation to make sense to us. Our brains evolved to understand medium-sized objects moving at medium speeds in a medium-sized world. We're good at tracking predators, finding food, building tools, navigating social hierarchies. We're not good at understanding quantum mechanics or the structure of the multiverse or the nature of nothing. Those are domains so far removed from our evolutionary context that it's honestly miraculous we can understand anything about them at all. And yet, when we push the boundaries, when we follow the math and the observations as far as they'll go, we keep running into ideas that violate our intuitions, that make no sense from an everyday perspective. The universe came from nothing, except nothing isn't nothing. The vacuum is full of particles, except the particles aren't real. Time doesn't exist before the Big Bang, except before doesn't mean anything without time. The multiverse is infinite, except infinity isn't a number. It's all deeply, profoundly weird, and there's no guarantee that any of it will ever feel intuitive or comfortable. This is the terrifying truth at the heart of reality. It doesn't care what we think. It doesn't care if it makes sense to us. It doesn't care if we can wrap our heads around it. Reality is what it is, and we're just passengers trying to make sense of a ride we didn't ask to be on. The universe might be infinite. It might be 1 of 10 to the power of 500. It might have come from nothing, or it might be eternal. We might never know for sure, and even if we do figure it out, the answer might be so alien, so disconnected from our everyday experience that it'll feel like nonsense. But that's okay. That's actually kind of liberating in a weird way, because it means we're not constrained by our intuitions. We're not limited by what feels right or makes sense. We can follow the evidence wherever it leads, even if it leads us to places that are uncomfortable, places that challenge everything we thought we knew about existence. And maybe, just maybe, by pushing into that territory, by confronting the strangeness head-on, we'll find something even more profound than answers. We'll find new questions, deeper mysteries, and a richer understanding of just how bizarre and wonderful this reality we inhabit truly is. So when you look up at the night sky, when you think about the edge of the universe and what lies beyond, remember this: the universe is stranger than you can imagine. It's bigger, weirder, more layered, more complex than any story we could make up. And at the bottom of it all, beneath the galaxies and the inflation and the multiverses and the string landscapes, there's a question that might not have an answer. What is nothing? And the best answer physics can give us is this: nothing is something. It always was, and it always will be. Reality is inevitable, existence is mandatory, and we're all just along for the ride. And honestly, what could be more terrifying and more awe-inspiring than that? So, where does that leave us? We started this journey standing at the edge of the observable universe, staring out at a cosmic horizon we can never cross, wondering what lies beyond. And what we found wasn't some simple answer, some neat explanation that ties everything up with a bow. No, what we found was layer after layer of strangeness, each one more unsettling than the last. We found that the universe doesn't have a center, that every point is equally valid, equally unimportant. We found that our observable bubble is probably just one region in an infinite expanse of space, where every possible version of you exists somewhere, living out every possible life. We found eternal inflation, creating infinitely many bubble universes, each one a separate cosmos with potentially different laws of physics. We found the multiverse hypothesis, this kaleidoscope of realities stacked on top of each other, from quantum branches to mathematical structures. And we found the string landscape, 10 to the power of 500 possible universes, each one a different configuration of reality itself. And then, after all of that, after building up this impossibly vast picture of existence, we asked the deepest question of all: what is nothing? And the answer we got back was terrifying in its simplicity. Nothing doesn't exist. It can't exist. The moment you have any kind of framework, any kind of rules, you've already got something. The vacuum isn't empty, it's seething with quantum activity. Space-time isn't inert, it's a dynamic, fluctuating foam, and reality itself isn't optional, it's inevitable. The universe exists because the alternative, true nothing, is impossible. So here's the thought I want to leave you with, the thing that should keep you up at night. We spent this entire video talking about the edge of the universe, about what lies beyond the cosmic horizon, but maybe the real edge isn't out there in space. Maybe the real edge is conceptual. It's the limit of what we can know, the boundary between the questions we can answer and the questions that might not have answers at all. Because even if we figure out the multiverse, even if we map the string landscape, even if we understand eternal inflation and quantum mechanics and the nature of nothing, we'll still be left with one final question that physics can't touch. Why is there a framework at all? Why are there rules? Why does anything exist instead of just not existing? And the honest answer is, we don't know. We might never know. That question might sit forever beyond the edge of human understanding, a mystery so deep that even our most brilliant theories can't reach it. And you know what? That's okay.